I think everyone sees the board. Please confirm me. Good evening. So please confirm me. So audio, just I'll increase. Now audio and other things are clear, right? Right. Done. So I think this, just let me, this black background is okay, I hope, right? So I'll be just discussing in this black background, right? So please confirm if it is okay. Black background, all of you. Right. Fine. Fine. I'll be discuss. Fine. So as my topic is induction machines, so just let me hide the volume, right? So volume is high now. So if anyone want to become, I mean to say, strong in machines, he or she should know some basic law, or I mean to say basic rules. So what are those basic law, basic rules means? So first I'll be starting with these basic laws or basic rules. After that, we'll be discussing our induction machines. So first I'll be talking about Faraday's law. So you can see, just 1 second, Faraday's law. So most of you may be knowing about this Faraday's law, but still I'll be discussing the basics. Why? Because tomorrow when I'm talking about the so-called the working principle, you are not supposed to question me again. The question again called as Faraday's law. So audio is clear. 1 second. So audio is maximum. See, one thing you please confirm me whether you need white background or black background. So basing on that, I'll go. So please just type it in the question and answers box. So according to you, I'll go. So black is okay. So black. See, some wrote white, some wrote black. So most of the people says black. So I'll go with the black. So in between, I'll go for white. You see which one is correct. Then accordingly, we can go for that. Right? Please let me start with black. So let me not disturb again. So Faraday's law. So you may be knowing Faraday's law, but still I'll be discussing Faraday's law once again. Right? After that, I'll be discussing what is called as Fleming's right-hand rule. Fleming's right-hand rule. Then I'll be discussing about Lorentz law. Lorentz law, or this is also called as Lorentz force equation. Then after that, I'll be discussing about Fleming's left-hand rule. Left-hand rule. Then I'll be talking about Lenz law. Then I'll be talking about right-hand thumb rule. Right-hand thumb rule. Right-hand thumb rule. Right. So these are the few things which you need to know before we start our class. See, some wrote black, some wrote white. So let me see black. After that, I'll go for white. You just see. No worry, right? We'll see. So don't type now. So it is over, black and white. Just we'll see now, right? Don't type now. We'll see. Now let me for also just you see which one is comfortable. Just give me 1 second. Now you tell which one is comfortable to you. So this is white and the previous one is black. Now you tell. So which one is better? Accordingly, I'll go. Black, sir. Black is better. Okay. So most of the people said black. So we'll go for black, right? See. Right. Black. So black is more comfortable in mobile, if I'm correct, right? Faraday's law. So what is this Faraday's law says? So most of you may be knowing the definition for Faraday's law. So what is the definition for Faraday's law? We'll see. Just let me select one color for today. Right. So what is that Faraday's law says that? So this Faraday's law says that if the flux linkages with a coil changes, due to that changes, an EMF is induced in that coil. So what are called as flux linkages? One has to know what are called as flux linkages. So if you understood what are called as flux linkages, then you can understand what are called as changes in flux linkages. Please remember that the EMF is only due to the changes in flux linkages. First, let me explain what are called as flux linkages. After that, I'll be discussing what are called as changes in flux linkages. Changes in flux linkages. Flux linkages. So always this EMF will be due to these changes. So EMF will be always due to changes. So I'll be explaining what are called as flux linkages. After that, I'll be discussing what are called as changes. Now, for your convenience, I'll be taking one permanent magnet. A permanent magnet. And you know that this permanent magnet will have a north pole and this permanent magnet will have a south pole. So because of these poles, we'll be having magnetic flux lines like this, like this. And you know from your 10 plus 2 or intermediate, the magnetic flux lines will originate from a north pole and they will terminate at a south pole, right? And to complete the path, the same magnetic flux lines will travel from south to north internally, right? So they will complete the path. So you know that. So what I will do means I'll consider one coil which is perpendicular to this. So let me consider this one as a coil perpendicular to this. Now, as of now, if you can see, the number of flux lines passing through that coil are 0. So there are no flux lines. Then you can see no flux lines here. No flux lines. Why? Because the coil is far away from a magnet. So you may have a doubt. So always we need to take a permanent magnet or any magnet. So if you are having a permanent magnet, you take it, or you can design an electromagnet. What is an electromagnet? We'll see, right? So you can see there are no flux lines now. But whenever I try to move this magnet, magnet closer to this coil, then you can see these flux lines will be traveling through this coil. So these will be traveling through this coil. So whenever I try to move this magnet very close to this, or if I try to move this coil closer to that magnet, then you can see the flux lines will start flowing through that coil. So what are flux linkages means? I can say the total number of flux lines passing perpendicularly through a given surface or through a coil, we call it as flux linkages. So let me consider this is our coil, and through this coil, how many flux lines are passing now? There are 5 flux lines passing. So what is the definition for that flux linkages means? The total number of flux lines passing perpendicularly through that coil represent the flux linkages with that coil, right? So if anyone questions you, how many flux lines are passing through that coil, means I can say the total number of flux lines passing through that coil are 5, right? See one thing, don't raise the hands as of now. Why? Because we'll be having the doubt discussion. So in this we'll be clarifying. So what is that, sir? Please tell, use other color. What is that other color? See, So whatever the colors available, I'll show to you. You please tell me that one. So you can see this is one color. This is one color. This is one color. Like this, we are having colors. So out of my experience, what I can say is the black color is the best color for mobile view, right? Please let us not have any discussion on this. I can see. So this black view is excellent. So there is no need to worry, right? Fine, right, fine. I'll increase the voice also. Fine. So this is something about your so-called as flux linkages. So what are called as flux linkages means? Flux linkages means, see the total number of flux lines which are passing perpendicularly through a given surface represent the flux linkages. So I'll try to change the color also, don't worry. Fine. So can I say what are called as flux linkages means? Flux linkages means the total number of flux lines passing perpendicularly through a coil represent the flux linkages, right? So if that coil is having say n turns, see some students told whiteboard, some students tell backboard. See, you conclude. So which one I have to discuss, right? Please. See, I cannot go with one right now. So we'll see. Just 1 second. Give me 1 minute. I'll come back to you. See, most of the students may have a doubt that so that PDF will have a black background. No. So the PDF will be white only. So, right, I'll go for white background only, don't worry. Right. So this is your white background. Let me change it to white. Right. And here, let me go for some lines also. Right. So I'll increase the size. Right. Flux linkages. I hope this is clear now. Now I think it is clear. So I have changed it to white. Right. So now you are comfortable with white, I think, all of you. Right. Now please don't disturb. Let me continue the subject. So what are called as flux linkages means, so if I'm considering a coil, and through that coil, the total number of flux lines represent the flux linkages with that coil, right? So in our case, how many flux lines are traveling now means we can see the flux lines are now 5. So tomorrow, if anyone questions you, or what are called as flux linkages means, what should be your answer means, if I am having a permanent magnet or electromagnet, and if I'm having a coil, and through that coil, if the flux lines are passing perpendicularly, so the total number of flux lines represent the flux linkages with that coil, right? Done. Now I should explain what are called as changes. Changes in flux linkages. What are called as changes in flux linkages. Changes in flux linkages. Please remember that what are called as changes in flux linkages. See, I'll consider for our convenience how many flux lines are here. 5 flux lines are here. So this is one flux line. So this is one flux line, and this is one flux line. This is one flux line, and this is one flux lines. 5 flux lines are there. Like this, I'll take some 5 instants of time. 5 instants of time I'll take. So this is one instant. This is one instant. I'll take 5 instants of time like this, right? Right. So how many flux lines are here? In each case, 5 flux lines are there. See, I'm trying to answer to the question what are called as changes in flux linkages. So here I'll consider one coil like this. I'll consider one coil like this. Coil like this, right? I'll consider this is one instant of time t is equal to t1, right? You can see when that coil is in position 1, how many flux lines are passing through that coil? 5 flux lines are passing. So the flux linkages with that coil are maximum. So how many flux lines are there? 5 flux lines are there. So all 5 flux lines are passing to that coil. So the total flux linkages are 5. Now what I'm trying to do means, with some external prime work, I'm trying to move this coil, rotate this coil. I'm trying to rotate that coil. So when I try to rotate this coil like this, say like this, I'm moving that coil like this. When I'm trying to rotate that coil, then you can see in this case how many flux lines are there? 5 flux lines are there. But when I'm trying to move this coil, then in this case how many flux lines are traveling now? Only 3 flux lines are traveling. So you can see from 5 flux lines, so the total number of flux lines are reduced to 3. That means there are some changes taking place. So out of 5, now how many are traveling now? Only 3 are traveling. So I can see there is some change. So here the flux linkages are not maximum. So the flux linkages have changed. Now what I will do means I'll try to keep this coil like this. Coil like this. When I'm trying to keep that coil like this, then you can see how many flux lines are traveling through that. The total number of flux lines are 0. So the flux linkages are 0. So changes delta n or delta lambda, changes are maximum. How can you say changes are maximum means? You can see for our convenience, we have assumed that how many flux lines are passing through that coil? 5 flux lines are passing. But when I'm trying to move that coil, you can see the total number of flux lines passed through that coil are changing. So during the instant of time t1, the total flux lines are 5. Now when I'm trying to move that coil, so you can see the number of flux lines are changing. So here, how many flux lines are there? 5. But here, here 3. How many are here? 5. But you can see the flux lines here are 0. So when the flux lines are 0, from 5, the flux lines are changed to 0. So out of 5, as they are becoming 0, so the change is the delta lambda is 5 here. So delta lambda is 0 here. Delta lambda is 2 here. So from 5 they are changing. So in which case that EMF will be maximum is, so in this case the EMF will be maximum. Why? Because according to Faraday's law, if the changes are maximum, the EMF will be maximum. Why? Because it is true that the EMF in a coil is not due to the flux link, but the EMF in the coil is due to the changes in flux linkages. So whenever the changes are maximum, the EMF induced in that coil will be maximum. So if anyone questions you, or in which position or at what time the EMF in that coil will be maximum, means you can answer blindly when the coil is in position 1, or during the instant of time t1, the EMF will be 0. When the coil is in position 3, or during the time t3, the EMF will be maximum. Why? Because the EMF will be always due to the changes in EMF, the changes in flux. Now if I move this coil further, then you can see again the changes is something like 2 here. So here the changes is again 0 here. If I try to bring back the coil back, so here, in which case that EMF will be maximum is, in this case the EMF will be maximum. So what is that? Faraday's law says that if the flux linkages, or in other way, if the number of flux lines passing through a coil changes, due to the changes in that, an EMF will be induced. So please remember, EMF is not due to the flux linkages. The EMF will be due to the changes in flux linkages. So in which case that EMF will be maximum is, the EMF will be maximum in time 3. So if I'm going to plot that, so it will be like this. So this is your instant T3. So this is T3. If I take, this is T4, this is T5. So this is like this. Like this, the cycle will continue. So can I give a statement? What is called as Faraday's law means, the Faraday's law states that if the flux linkages with a coil changes, due to the changes in flux linkages, an EMF is induced in that coil. So whenever the changes are maximum, then the EMF induced in that coil will be maximum. So whenever the changes are minimum or changes are 0, the EMF will be 0. So I'll give the statement like this. What is that statement? If the flux linkages with the coil are changing due to the changes in flux linkages, an EMF is induced. An EMF is induced. EMF is induced, right? So by how many ways we can change the flux linking with a coil? So there are 2 ways. What are those 2 ways means? One is dynamically induced EMF, or dynamically way. The other one is statically induced EMF. right? Statical induced EMF, right? There is no S. So statical induced EMF. So what is called as a dynamical induced EMF? I think this concept you might have come across in your generators. What is that in generators? So we'll be having magnet, magnet, magnet like this. And with respect to this magnet, we'll be having magnetic flux lines. Magnetic flux lines. So in this magnet, so here, what we'll try to do means we'll try to move a coil. I'm not drawing a armature or something like this. I'm taking a coil like this. Coil like this. You can see when the coil is in this position, when this coil is in this position, the EMF will be zero. Why that EMF will be zero? You can see all the flux lines are passing through that coil. But whenever I try to move this coil, whenever I try to move this coil, you can see the conductors are moving. When the conductors are moving, you can see the flux linkages with this coil will change. So due to the changes, an EMF is induced. So in case of your generators, what is that we are trying to do means, so we will be having a stationary magnetism, we'll be having a flux lines, and in that flux lines, we'll be continuously moving the coils. When we are continuously moving the coils, the flux linkages with that coils will be changing, and due to the changes, an EMF is induced in that coils. So if you recall in your thermal power stations, or in case of hydel power stations, or a diesel, whatever it may be. So what is that mechanism we are trying to do means, if I'm talking about a stationary magnetic field arrangement, so there the field system will be stationary, and in that the coils will be continuously moved. Coils will be continuously moved. So who is moving that coils means, so that coils will be connected to some external prime mover. In case of thermal power station or steam power plants, what we are trying to do means we'll try to burn the coal, and that coal energy, that heat energy is used to boil the water, and that is converted into steam, and that steam is used to heat the blades of the turbine. So when steam is hitting the blades of the turbine rotates. As that coil is connected to that, the coil will also rotate. Whenever the coil rotates, so that's linkages, that coil will change, and due to that, an EMF will be induced. So this we call it as dynamical induced EMF, right? Right. See, Baba. So voice is clear. See, don't raise the hands. I told you that. So whenever I give time to discuss the doubts, you can discuss, right? Please. Fine. Right. Right. So this is something about your dynamical induced EMF. What is a dynamical induced EMF? So in case of your generators, so the field system is stationary. I'm talking about statically or stationary magnetic field arrangement. The field system is stationary, and in that stationary field system, the coils are continuously moved. When the coils are continuously moved, then the flux linkages with that coils will change, and due to that, an EMF will be induced. But if you open it, so in that there will be a definition called, whenever the conductor cuts the magnetic flux lines, an EMF is induced. But you can see here, when I move this coil, so these conductors will move. So whenever those conductors move, so those conductors will cut the magnetic flux lines. So whenever those conductor cuts the magnetic flux lines, an EMF will be induced. So you should note a point here that whenever the statement is given that the conductors are cutting the magnetic flux lines, whenever the conductors are cutting the magnetic flux lines, it is understood that the flux linkages with that coil are changing, and due to that, an EMF will be induced, right? See, such type of questions you are not supposed to ask. How many marks for this? Like that. See, please just wait. Right. So I'll keep. Don't fine. I can understand the problems. Right. Fine. You can see. So this is something about dynamic. I'll go back. So what is called as a dynamical induced see first day some 1 hour we'll be having such things. After that we'll settle down. Don't worry. And anyhow this PDF will be sent to you. Absolutely no issue. Right, please. So what is that dynamical induced EMF means? Here in case of this dynamical induced EMF, the coils will be moving. When the coils are moving, so the flux linkages with that coils will be changing. So due to that changes, an EMF will be induced, right? So if you go for any standard textbooks, so they may not use this terminology, the changes. So they will say whenever the conductor cuts, whenever the conductor crosses the magnetic flux lines, an EMF will be induced. Then you know that whenever a coil is moved, so those conductors will be cutting the magnetic flux lines. When those conductors are cutting the magnetic flux lines, EMF will be induced. So this we call it as dynamical induced EMF. So why the name dynamical induced EMF has come is as the coils are moving, as the conductors are moving, so the moving conductors are able to have an EMF in that. So that is the reason these are called as dynamical induced EMF. So can I say, so here in case of this dynamical induced EMF, so EMF is due to flux cut or flux cutting. Flux cutting. So how that flux lines are cutting means, so whenever a coil is moved, the conductors are moved. Whenever the conductors are moved, so those conductors are cutting the magnetic flux lines. So can I say, so just I'm going for, so in case of dynamical induced EMF, the coils are moved in a stationary magnetic field due to this the flux linkages with the coil changes due to this an EMF is induced. So where we use this concept of dynamical induced EMF means we'll be using in case of generators. So don't raise the question that, sir, whether it is a AC generator or a DC generator. Please keep this in mind. So the law which governs the generator is not different. Maybe a DC generator or maybe an AC generator, they work on only. So basing on the requirement, whether I need a DC output or AC output, the construction or the manipulation is done. So please remember that. So this is something about your dynamical induced EMF. So sir, only whenever the conductor cuts an EMF or cuts the flux line, an EMF is induced. But if you go back to the transformer, in case of transformer, there is no concept of flux cutting. Then how can you say that an EMF will be induced in case of your transformer? Now, so that we talk under statical induced EMF. Right? I'm just scrolling down. Please go through statical induced EMF. What is that statical induced EMF means? See, already I told you that magnetic flux means it is nothing but the group of flux lines. More is the magnitude of flux, more are the flux lines, less is the magnetic flux, less are the flux lines. Now if I'm taking this one as the magnetic flux, let me consider, so which is varying with respect to time. So this is the peak value of flux. So I'm considering one coil here, a coil here. So if anyone consider, or what is the magnitude of flux at this instant of time t is equal to 0 means the flux is 0. When the flux magnitude is 0, so if I'm trying to pass this flux here, so the total number of flux lines passing through this is 0. But if I consider one instant of time t1 here, you can see the flux magnitude is increasing. Flux magnitude is increasing, the total number of flux lines passing through that coil are increasing. So here you can see the flux magnitude is more. When the flux magnitude is more here, so the number of flux lines passing that coil are increase, right? You can see the number of flux lines are increase. If I consider an instant of time t is equal to t2, the flux magnitude is maximum there. When the flux magnitude is maximum, then you can see the total number of flux lines passing that coil are maximum. So can I say with respect to time, as the flux magnitude is changing, and the same flux lines or flux is passing through that coil, the total number of flux lines passing through the coil are also changing. So due to the changes, an EMF is induced in this coil. So it's not like compulsory that, so for an EMF, the coils has to be moved. So the coils can be stationary or the coils can be moving. So the condition, when the coils are stationary, the flux which is passing through that coil should be having time varying nature. So the magnitude should be varying with respect to time, right? So this is something about your statical induced EMF. So can I say in case of statical induced EMF, the coils are stationary, but the flux which is passing through that is varying, the magnitude is varying with respect to time. So it may be static induced EMF or it may be dynamical induced EMF. So the EMF is only due to the changes in flux linkages. So if anyone questions you by how many ways we can change the flux linkages, means there are two ways. The first way is with a stationary field, moving coil. The second way is the stationary coil and time varying magnetic field. See, I don't know what are the questions you are having. See, voice breaking means it is not from my side. Please, right? Right. So this is something about your Faraday's law. So what is that statical induced EMF says? I'm writing. Please go through this. In case of statical induced EMF, coil is stationary, but the flux magnitude is varying with the time. Right? So this is something about your Faraday's law. Let me once again recall and revise. What are called as flux linkages means see, there is no disturbance from my side, Dasarath Reddy. So I'm just closed and AC field here, right? Please. So my from my side everything is clear. Please try to rectify from side. I'm clear with my side, right? Fine. Please go through that. See, everything is clear from my side. See, network is clear and everything is clear. Now it is clear. It is breaking still. Please confirm me. Still it is breaking or it is clear?
Sir, we don't have any issue, sir. Sir, students got. Yes, sir, yes, sir. We don't have any issue.
Right. Thank you, sir. Right. See, I'll repeat. So we are able to complete this Faraday's law. See, flux linkages. What is the meaning of flux linkages? Means if I am having a magnet electromagnet, and if the flux lines produced by that magnet or electromagnet, if they are passing through a coil, then that represents the flux linkages. But EMF is not due to that flux linkages. That EMF will be due to the changes in flux linkages. So by how many ways we can change the flux linkages means by two ways. What are those two ways? Take the field system to be stationary, and in that you move the coil. That is one way. In the second case, see that the coil is stationary and the flux which is passing through that is varying. The magnitude is varying with respect to time. Then in both the cases, the EMF will be induced, right? The best example is dynamical induced EMF. We'll use it in case of generators, and the statical induced EMF used in case of your transformer. Sometimes in a particular coil, an EMF will be induced due to statically, due to dynamically. We'll see what is that later on. So this is something about Faraday's law. The next one is Fleming's right hand rule. So just I'm scrolling down. So what is that Fleming's right hand rule means? So in case of dynamical induced EMF, if you want to know the direction of induced EMF, we'll be using this Fleming's right hand rule. So what is that Fleming's right hand rule says? That means if you want to know the direction of induced EMF in a particular conductor, then with respect to that conductor, you should know two things. One is in which direction the magnetic flux lines are traveling, and in which direction that conductor is moving. So if you know these two things, then with respect to the middle finger, with respect to the third finger, we can apply and we can find out the direction of induced EMF. So if anyone questions you, are you using Faraday's law? Is it possible to know the direction of induced EMF? No. So Faraday's law states that if you want to have an EMF in a particular coil, you need to satisfy these conditions. What are those conditions? See that there is a magnetic field, stationary magnetic field, move the coil in that, then an EMF will be induced. If you are not having a stationary magnetic field, if you are having a alternating magnetic field, see that you are placing a coil in that path, then an EMF will be induced. So in which direction that EMF or what is the polarities that Faraday's law will not give. So if you want to know the direction of induced EMF, we should apply Fleming's right hand rule, right? So next point is to know the direction of induced EMF. To know the direction of induced EMF, Fleming's right hand rule is applied. Fleming's right hand rule is applied. So what is that Fleming's right hand rule means? Already you may be knowing in case of DC, it is a basic rule. Basic rule. What does that means? So if you take the first three fingers of your right hand, first three fingers means please remember the thumb, the forefinger, the middle finger. If you place these three fingers mutually perpendicular to each other, with this forefinger pointing the direction of field, this thumb pointing the direction of motion of the conductor, then this middle finger gives the direction of induced EMF. But if you want to indicate the direction of induced EMF, please remember that you have to use some standard symbols. What are those standard symbols? One is cross, the other one is dot. So as a cross in our terminology indicates into. So if you are assuming that in the whiteboard there is one conductor, and if the flow of current is into, then you have to put cross. So it is a cross. Dot means outwards. So on what basis this cross and dot are being designed means you take a arrow. And if you release that arrow and if you see the arrow from behind, what is the symbol you come across? Cross. That means with respect to your eyes, if the current is flowing into the board, it is cross. And if the same arrow, if it is coming toward eyes, right, is try to escape, But what is the symbol you can see? It is a dot. So like that dot means the flow of current is outwards, right? So I'll give the statement, what is called as Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand rule. Right hand rule. So what is that? If the first three fingers, if the first three fingers of the right hand are stretched mutually perpendicular to each other, perpendicular to each other, to each other, with forefinger pointing the direction of magnetic field, comma, thumb pointing the direction of motion of the conductor, motion of the conductor, then the middle finger gives the direction of induced EM, induced EM, direction of induced EM. So this is something about your Fleming's right hand rule. So just give me 1 second. I'll try to show what is called Fleming's right hand rule. Just give me 1 second. You can see here. Fleming's right hand rule. You can see here. You can see this is the right hand, and this right hand is stretched, and the first three fingers are stretched mutually perpendicular to each other. You can see here, you can see here, this forefinger is in the direction of field. Forefinger is in the direction of field. The thumb is in the direction of motion of the conductor. Then this gives the direction of induced EMF. For example, say this is a north pole and this is a south pole. The magnetic field lines will be always traveling from north to south. So if you are trying to place your forefinger in this direction, then this conductor is moved in upward direction. Then what will be the direction of induced EMF? So this current will flow like this, like this, like this. So if you are putting a I here, then what is the symbol you can put here? Cross. Or if you are putting a I here, what is the symbol you can put here? Dot. So you can see, basing on the flow of current, basing on the position where you are standing, you can put cross or dot. It is not like always cross and dot will be fixed, right? So can I write like this? See, I'll take. So this is the magnetic field. Let me consider magnetic field. Let me consider. These are the directions, or these are the flux lines, right? And here in this, I'll have one conductor. One conductor is like this. Conductor is like this. I'm moving this conductor in this direction. In which direction? I'm moving in clockwise direction. Now I want to know the direction of current in this. So if I want to know the direction, the direction of current may be like this or the direction of current may be like this. I want to know whether the current is flowing in or out. So for that, I should apply Fleming's right hand rule. So what that Fleming's right hand rule says that, so with respect to this conductor, if you want to know, then first you should know the direction of flux lines. Direction of flux lines. So direction of flux lines. So you can see the direction of flux lines are downwards. Downwards. Direction of flux lines are downwards. Then in which direction the conductor is moved? The direction of motion of the conductor. Direction of motion of the conductor. In which direction we are moving? It is moving in, say, clockwise direction, right? Clockwise direction. So if I apply the right hand thumb rule, so what will be the direction of induced EMF? The direction of induced EMF will be cross. So if you are standing on the front side, you can see the flow of current will be into. So you can apply the right hand. So you can see the forefinger is downwards, the thumb is clockwise. What is the direction of induced EMF means? It is into the conductor. So this is something about Fleming's right hand rule. So please try to make a point here. Fleming's right hand rule will not tell how an EMF can be generated. So it will tell the polarities or the direction of that induced EMF. Please try to separate and don't mix. So don't mix Faraday's law and Fleming's right hand rule. Most of you may not be having the clarity in this. Right hand rule will give the direction. Faraday's law will tell the conditions to produce the EMF. So once again, so what is that Fleming's right hand rule says that if you are having a moving conductor, and in that moving conductor, if there is some EMF induced, so if you want to know in which direction that current will flow, means you have to apply this Fleming's right hand rule. So what that Fleming's right hand rule says that if you stretch the four fingers mutually perpendicular to each other, with the forefinger pointing the direction of field, the thumb pointing the direction of motion of the conductor, then the middle finger gives the direction of induced EMF, right? So this is something about Fleming's right hand rule. So next one is, see, before we go for Lorentz law, so many times we come across these terminologies, theory and law. So some areas of the machines you can find theory, some areas you can find law. The best example is Faraday's law and rotating magnetic field theory. Now my question to you, if anyone can answer, right? What is the difference between a theory and a law? Theory and a law, right? So just I'll be looking into this question and answers. If anyone knows, please answer. What is the difference between theory and a law? It is 6 now. I have to see 6 o'clock time. Wait, I'm just looking. Right. See, in statical induced EMF, flux cutting action take place. See, Murlidhar, no, in case of statical induced EMF, there is no concept of flux cutting. Please remember that flux cut means the conductor should be moving, right? Please remember that. But whereas in case of your so-called as transformer, a statical induced EMF, the conductors are not moving, right? Right. So law is proved once, sir, right? Once again, the direction in which direction? Okay. Law is undisputable. Okay. Law is universal. Law is universal accepted one. Law has a proof. Law is proved practically. Excellent. Law is always right. Theory may be hypothetical. Okay, right. Very good. I'll explain. Excellent. See, I'll answer to this question. Law, as most of you have written, law is actually true always. Law is actually true. Why? Because whatever the law we give generally basing on the experimental result or experimental output. Faraday's law. What is that? Faraday's law says that if you move a conductor in a magnetic field, an EMF is induced. Even if you can do the same thing now, experimentally, you can see that if you connect a voltmeter across a coil, when you move that coil, there is an EMF induced. That means it is always true. So this law will be always true. So there is no doubt in that law can be false. Law is always true. There is no doubt, right? But theory may be true, may be false. Why? Because theory is not basing on a practical result or experimental result. It is basing on some evidences. Some evidences we go for theory. So the best example what I can give is Darwin's theory of human evolution. So some theory was given by Darwin. So in that 80 to 90% are absolutely correct. So why life has begun with water, absolutely correct. But there is some contradictory statements in that. What is that? The human race, the humanity, the humans have started. So like our ancestors are like apes. So due to the gradual change in the environment, the human structure has been changed. So we are not like as we are now. So we are something like apes or chimpanzees. Our ancestors are like that. So with a gradual change, the system has the personality, the person has changed. So it is the statement given by Darwin. So in those days, people used to believe, yes, our ancestors may be like apes. So slowly there is a change. Why? Because the Darwin has not seen our ancestors. No one has seen the first generation, the first person, right? No one has seen. So in those days, people used to believe, yes, yes, it may be the reason. So our ancestors may be like apes, but now we are like this. But those who believes it is a belief, those who doesn't believe, so it is not a true. So theory may be true or theory may be false, right? So we cannot always trust a theory. So we can trust a law always. So theory cannot be trusted. So if you want to prove that your theory is correct, there has to be some mathematical equation, mathematical proof. If your theory is mathematically proved, then we can believe in your theory. Otherwise, we cannot believe your theory. So something like, the prediction of coronavirus, the waves. So some mathematical modeling they will do. Why? Because no one has seen what has happened in the month of August. So they will go for some modeling. So some theoretical, some model they will do, and they will tell, okay, during this time, so this will be reduced. So theory may be true, may be false, but law is always true. So please remember, if anyone questions here, what is the difference between a law and a theory means, law is always true, theory may be true or false, right? So this is something about your Fleming's right hand rule. Now the next one is Lorentz law. Sometimes it is also called as motor law. Lorentz law, it is also called as motor law. Motor law. Motor law. So what is this motor law or Lorentz law says? That means if you place a current carrying conductor in a magnetic field, so that current carrying conductor will experiences a force. Experiences a force, right? So can I give a statement? If a current carrying conductor is placed under a magnetic field, it experiences a force. What do you mean by that? I'll take an example. See, what do you mean by that? See, I'll be taking a north pole, and I'll have magnetic flux lines. Magnetic flux lines. So in this, I'll be placing one conductor. I'm not drawing this is one conductor. So this conductor is not carrying any current. When that conductor is not carrying any current, so there is no force acting on the conductor. But whenever I try to pass a current in this conductor, so that conductor will experience as a force. So what is the reason for force? Means I'll tell you one thing. So if we just recall right hand thumb rule, right hand thumb rule. What is that right hand thumb rule? Means if a current carrying conductor or if a conductor carries current, so that current carrying conductor will produces magnetic field. So if you want to know the direction of that magnetic field, then you need to call upon right hand thumb rule. So I think you may be knowing about Oersted, right? He was the first person to believe that the magnetism can be produced artificially. So till the time, till that Oersted, people used to believe that the magnetism can be had only with the help of a permanent magnet. The magnet, the core which is available naturally. But with Oersted, so he concluded that even magnetism can be produced artificially. How means? So during his time, Oersted, he was doing one experiment. So it is true. This is a fact. Why? Because most of the things will come like unfortunately. You take Newton's law. So there was a story built. So Newton was sitting below a tree when apple fell down. Then the gravity concept came. So like this, whatever the concept it may be, it is due to some things which are happening, right? Unseen things. What is that? See, Orested was doing one experiment in the laboratory and a compass. So in olden days, we used to have a compass, and in that a permanent magnet needle was there. So a compass was lying next to a conductor. So when he starts applying current through that conductor, then he observed that that compass needle was showing some deflection. He could not understand why when he starts applying passing current through that conductor, that compass needle was deflecting. He could not understand. Then he was like scared, something like devil or something like has happened. What may be the reason? Then during that time Faraday was there, so if I'm correct, so he discussed. Then after some series of experiment, he concluded that a current carrying conductor can produce as a magnetism. So he was the first person to prove experimentally that even magnetism can be produced artificially with the help of a current carrying conductor or a current carrying coil. So there is a difference we'll see in the coming days. So a current carrying conductor can produce as a magnetism. And if you want to know the direction of that magnetic flux lines due to that current carrying conductor, you should apply right hand thumb rule. So what is that? If I'm having a conductor which is carrying current in upward direction, if I want to know the direction of field, then you place your thumb in the direction of current in that, then the remaining four curved fingers will give the direction of magnetic flux lines, right? So this was given by right hand thumb rule, right hand thumb rule. See, so here, whenever I pass a current through this, so this current carry conductor will experience as a force, right? So can I say if a current carrying conductor is placed under a magnetic field, it experiences a force. Now the question comes, why when that conductor is carrying current will experiences a force? There has to be some reason. Without that reason, there is no force. So when I switch off this current, so that conductor is coming back, it is not experiencing any force. The reason for that is, now see, you take current, you take water, general example, water. So if you pour water on a plain surface, then if you watch that water, then you can see that water after some time will be moving in a low height areas. That means compared to that surface, that water will find the low height or low potential area, and that water will try to settle down in the low potential area. Sometime you might have come across some statement. So there was some heavy rains, but only one particular area is like sink, that there is one particular area is flooded with water. What may be the reason means it is not like heavy rainfall is in that particular place. The reason is the rainfall will be there throughout the region, but particularly that area will be at low heights. So all the water is collected in that area, and that area will be flooded. So every water will try to settle down in low height areas. And even if you try to take a current, what is the basic property of a current? So more current will flow through a low resistance path. So always current will try to take a low resistance path. Similarly, if you try to take a magnetic field or magnetic flux lines, so those magnetic flux lines will always try to take a low reluctance path. Now you can see here, when I'm not passing any current through this, so what is the direction of magnetic flux lines? The direction of magnetic flux lines are straight. So the magnetic flux lines are straight. They are straight. So they are straight means they're taking the low reluctance path. But when I place a conductor here, and when that conductor is carrying current, then what happened now? So due to that current carrying conductor, we are having magnetic field lines. So if I want to know the direction of magnetic field lines, then which rule? Right hand thumb rule. You can see the current is flowing into the board. The direction of flux lines will be like this, clockwise, like this. Now these magnetic flux lines which are supposed to travel straight, because of this magnetic flux lines, they are taking the longest path. I'm not drawing a smooth curve, try to understand. Longest path, like this. Now these magnetic flux lines will say, you stupid fellow, because of you and your current, we have one more flux lines, and because of your flux lines, we are forced to take the longest path. No. It is against our property. We cannot take the longest path. Please move from this position. Please get away from this position. So we want to come back to our original position, that is the straight position. As a result, that conductor will be moved away. From that position. Why? Because those flux lines want to come back to their original position. So that is the reason that conductor has to move from its position. General example, you take a cat ball. If you try to stretch the cat ball, cat ball. When you try to stretch a cat ball, then on your hand, you can see there is a force acting. What is that force acting? That elastic nature will say, you leave, we want to go back to normal state. You leave, we want to go back to normal state. Here also, so this current carrying conductor is producing one more flux lines, and those flux lines are making that original flux lines to stretch. They are trying to stretch, but those flux lines say, so no, we cannot stretch, please move from our position. So those flux lines will be inserting a force, and hence that conductor will try to move away from its position. Is this point clear? Confirm me, all of you. Raise the hands. Right. So can I say, if a current carrying conductor is placed under a magnetic field, so that current carrying conductor will experience as a force. If tomorrow, if anyone questions you why that conductor has to experience as a force, means you have to answer, are you persons, you people, are it is a simple physics, it is a simple concept. So the magnetic flux lines, when there is no current through that conductor, they are taking the least reluctance path, low reluctance path, they are traveling straight. But whenever you try to pass a current through that conductor, so those current carrying conductors are producing one more flux lines, and these flux lines are trying to stretch that original flux lines. So they are forced to take the longest path. No. So they have to come back to their original position. So for that, the position of the conductor has to be moved, and the conductor will be moving away from its path, right? So this is something about, one second. So here the time is somewhere missing. Right, anyhow. So this is Lorentz law. Now in which direction the conductor will move means that is given by your Fleming's left hand rule. So Lorentz will not tell in which direction that conductor will move. I don't know. So Fleming's left hand rule will give in which direction that conductor will move. For that, I have to apply Fleming's left hand rule. You can see this. One second. Yeah, statement I'll give everything. So already I have given the statement, right? If a current carrying conductor is placed under a magnetic field, it will experience as a force, right? Sir, can the curved path be still low reluctance path? So this path is not a low reluctance path. So low reluctance path is the straight path. Please remember, Kiran, it is the straight path, right? Right. Fine. Right. This is something about your so-called as Lorentz law. Once again, I repeat. So what is that Lorentz law says? That means if a current carrying conductor is placed under a magnetic field, so the current carrying conductor will experience as a force. Now the question comes, why the current carrying conductor will experience as a force means, so because of that current carrying conductor, we have one more magnetic field. Because of that, the original magnetic field is taking the longest path, and so that magnetic field will be having a force on the conductor, and hence the conductor will be moving from its position. So this is very similar to your cat ball. When you try to stretch the cat ball, then you can see if you put any object there, so when you try to release that, so that object will try to move. The same logic here. So if the magnitude of current is more, the stretching will be more. When the stretching is more, the force exertion will be more. So like that, the conductor will have more force, right? Done. See, if you have any doubt how to contact you, sir. See, Baba, I don't know, you'll be having doubt clarification session. So from 8:30, like that, I'll be discussing half an hour. So whatever the doubts you have from today's class, I'll discuss. Don't worry, right? Naresh Nayak. Naresh Nayak. Okay, fine. Magnetic flux lines of magnetic lines of force, closed path. Yes, correct. Fine. Next one is to know the direction of mechanical force. I'll write the statement. To know the direction of the mechanical force, Fleming's left hand rule is used. Left hand rule is used. Rule is used. See, Lorentz will not tell the direction of moving of the conductor. So if you want to know the direction, then you have to call upon Fleming's left hand rule. What is that Fleming's left hand rule says? See, if I'm having a magnetic field, I'll give the statement, don't worry. See, for everything, I'll give the writings, don't worry. I'll give the writings. If I'm having a north pole, say these are the magnetic flux lines, and I'm having a conductor, and this conductor is carrying a current like this. Now the question comes, so this conductor will try to move in this direction, or this conductor will try to move in this direction. So for that, I need to call upon which rule? I have to call upon Fleming's left hand rule. So what is that Fleming's left hand rule states? That means, so I'll give the statement here. If the first three fingers of the left hand are stretched mutually perpendicular to each other, with forefinger pointing the direction of magnetic field, middle finger pointing the direction of current, then thumb gives direction of mechanical force, right? So you can see with respect to this, the field lines are downwards, the direction of current is into, Then if apply the so-called as left-hand rule, then the force will be like this. So in which direction this conductor will move means it will move in this direction, not in this direction. So this is something about Fleming's left-hand rule. So please, Baba, understand the difference between Fleming's left-hand rule, Lorentz law, right-hand rule, Faraday's law. Faraday's law will provide the necessary conditions to produce voltage. Fleming's right-hand rule will facilitate to tell the direction of induced EMF. Lorentz law will tell the conditions to produce the force on the conductor. That means the current carrying conductor has to place under a magnetic field. Then Fleming's left-hand rule will tell in which direction that force will be acting. Please try to separate, don't mix up. The last and very, very important thing is the Lenz law. The Lenz law. So this Lenz law is very, very important. And using this Lenz law, even we can find out the direction of statically induced EMF. And even in case of motors, we can find out the direction of rotation, right? So this Lenz law can use it to know the direction of statically induced EMF, or even using this Lenz law, we can find out the direction of rotation. That also we'll see. So what is this Lenz law states that the effect opposes the cause. Effect opposes the cause. I'm not giving a lengthy statement, right? The effect opposes the cause. So this one line statement carries a book of knowledge or book of concept. So I don't want to discuss all the things required for, all the things about Lenz law, but what is required for us, I'll be discussing Lenz law, right? So please remember that this Lenz law is even applicable in your normal life also. So in every individual life, this Lenz law is applicable. You'll be shocked to know what is called as Lenz law. It is something extension of your Newton's third law. For every action, there is equal and opposite reaction. The same thing. What is that Lenz law? We'll see. Just give me just 5 minutes. I'll explain. So what is this Lenz law states, sir? Please see. So here, what I will do means, I'll consider one coil. So in that coil, there is one conductor. Let me consider there is one conductor. So this is one conductor, right? So the front conductor I'm showing like a pipe. This is one coil. So this is one coil, right? Coil with a switch. So this is a coil. So I have to draw this like this also. I'm not drawing this. This is a coil. I'm considering one conductor here. So let me call this conductor as AB. 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 So this is a switch, right? So what I'll try to do means, I'll try to take a magnet. I'll try to take a magnet. Please understand this. I'll try to take a magnet. And this magnet is far away from this coil. As this magnet is far away from this coil, see, these magnetic field lines will always exist in closed path. That means from north to south, they'll exist in closed path. I'm not drawing that. Please understand this. So you can see these are the magnetic flux lines, and this magnet is far away from that coil. If I'm calling this one as a magnet, so this is a coil. So the magnetic flux lines are away from that coil. So here the flux linkages are zero. The flux linkages are zero. Now what I'll try to do means, with some mechanical arrangement, I'll try to move this magnet. When I try to move this magnet, so this magnet will come like this. It will come like this. When it is coming like this, as that magnet is approaching the coil, you can see the magnetic field lines will try to flow through the coil. So the magnetic flux lines are trying to flow through the coil. So initially, when the magnet is far away from the coil, the flux lines are zero. But when the magnet is coming closer to the coil, so the flux lines are trying to flow through the coil. That means the flux linkages with that coil are changing. So initially, how many flux lines are flowing when the magnet is far away? So the flux lines are zero. But when the magnet is coming closer to that coil, the flux lines are increasing. They are changing. So whenever that magnet is coming closer, so due to the changes, an EMF is induced in this coil. So what is that effect? Means the EMF. So if anyone questions you, you said that the effect should oppose the cause. So in this case, what is that effect? Means the effect is the EMF. So here EMF is the effect. So why an EMF is induced in the coil? Initially there is no EMF induced, but whenever that magnet is coming closer to the coil, then you can see that coil is having some EMF. So effect is EMF. So why there is an EMF means due to the changes in the flux linkages. So initially the flux linkages were zero when the magnet is far away, but when that magnet is coming closer to that, then obviously the flux lines are started flowing through the coil. Due to that, the changes are taking place, the flux lines are changing. Due to the changes, an EMF is induced. Is this point clear? Confirm me, all of you. Raise the hands. Right. Now what that EMF has to do means, no, it has to oppose that. What is the meaning of opposition means? That EMF should become zero again. There was no EMF initially, so as the flux line started flowing through that, as there is some EMF induced, so that EMF has to come back to zero again. But here EMF is an electrical property. It is an electrical quantity. So EMF cannot directly oppose the flux lines. Why? Because the flux lines are magnetic parameters. So EMF is an electrical parameter. Then how means, for example, if this switch is closed, and as EMF finds a closed path, so a current has to circulate. Then you can see this current carrying conductor placed under magnetic field will experience as a force, and due to this force, what should happen? Right? What should happen? So I'll tell. So once again, when that north pole is coming closer to that coil, an EMF is induced. So here EMF is a electrical parameter, so that EMF has to oppose the magnetic flux lines, but it is not happening. So how, if the switch is closed, then that EMF has to circulate a current. Then that current carrying coil placed under a magnetic field should experience as a force. Force means, what should be the role of that force means, that force should see that the north pole should not come closer to this. Why? Because an EMF is due to as the north pole is coming closer. If this force is opposing that north pole not to come, then that north pole will not come closer. Then the flux linkages with this coil will not change. When the flux linkages are not changing, there is no EMF induced. So if this force should have act means, so what should be the pole that has to be formed here? There should be a north pole formed here. If there has to be a north pole formed here, then the magnetic flux lines which should come out, or they have to be go in out. So the magnetic field lines has to come out like this. If the magnetic field lines has to come out like this, then I have to apply your right hand thumb rule. So if this thumb is in the direction of magnetic field, then the forefinger should give the direction of current. So in which direction this current has to flow means the direction of current should be like this. So the direction of current should be like this. So if the flow of current in this conductor is from B to A, then obviously, so the flux lines passing through that will be decreased. When the flux lines are passing through the decrease, then the flux lines become zero. When the flux lines become zero, the changes become zero. When the changes become zero, the EMF becomes zero. Right? It is something, can I say? So the intention of that north pole is to increase the flux lines passing through that coil. But this coil is saying, no. The initial flux lines were zero. I'll try to see that the flux line should remain zero. I'll reject you. I will reject you. You don't pass through the coil. Please get out. You don't come. I'll reject you. So as they are rejecting, so they are not allowing the flux lines to flow. How? Means, so it is simple mechanism. I can tell in many ways. In one example, what is that? So as the North pole is coming closer to that. The flux linkages with that coils are changing, and due to the changes, an EMF is induced. If the circuit is closed, the induced EMF will circulate a current. So the current carrying conductor placed under a magnetic field will experience a force of attraction, force of repulsion. Now, which one should act now? The force of repulsion should act. Why? Because the EMF is due to that magnet coming closer. So this force should allow, no, 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 you cannot come. Please go out, go back. So as the North Pole is coming here, what should be the pole that has to be formed here? A North Pole. If there has to be a North Pole, the flux line should come out from that. If the flux lines has to come out from that, so what should be the direction of current in that coil or in that conductor? Means it should be from B to A. If the direction of current is from B to A, then the EMF magnitude will be reduced, right? So is this point clear? Confirm me all of you. Is this point clear? Confirm me all of you. All right. Right. One student asked, sir, can we expect? See, Baba, one thing. See, I request you all. I'll be spending some time on doubts. See, every time I cannot go through this question and answers. My humble request to all, I'll be giving time for doubts clarification, right? Whatever the doubts you have, please write it on a paper. So whenever we have these doubts discussion today after end of the class, you can clarify. So this question and answers, you please try to make use for something like if you're not able to listen my voice or something. For that, you please. Then when I give some time for the question and answers, you can type the questions. Then I can look at the questions, I can give the answers. Please, why? Because multitasking cannot be done by a human. I cannot concentrate here. See, whenever I give a time, please try to question your time, right? Please understand that. See, why don't we use South Pole? You can use South Pole also, no issue. Dot convention also you can use, right? Yeah, how to B to A? Yeah, so that question, so I'll repeat n times, no problem. Anonymous attendee. See, if I'm assuming this is your conductor, so this is point B, this is point A. Now the magnetic flux lines has to come down. So if the magnetic flux lines has to come down means the flow of current should be like B to A. So the flux line should be down. The flux line should be down. So in which direction the current has to flow? Like this. If the current is flowing like this, the flux lines will be in downward direction. So like that, the EMF, that current will be circulating. In other way, I'll tell you. In other way, I'll tell you. See, the current doesn't become zero again, right? Fine. I'll explain, don't worry. See, don't worry, I'll repeat n times. I know that this is a little bit typical topic. You can understand, right? Don't worry. I'll tell. Don't worry. See, many ways we can discuss. See, initially, this magnet is away from the coil. As this magnet is away from the coil, the total number of flux lines passing through that coil are zero. The flux associated with that coil is zero. So when the flux associated with that coil is zero, there are no changes. There is no EMF inducing that coil. But whenever you try to move that magnet, maybe North Pole or South Pole, whenever you try to move that magnet, then you can see that through that coil, the flux lines will start traveling. The flux lines will try to flow. Whenever the flux lines try to flow, what happened to that coil? The flux lines or the flux linkages with that coil will change. So due to the changes, what is induced in that coil means an EMF will be induced. So what is the effect that is happening means it is the EMF. So who is the main cause for that EMF means to come closer. So what this EMF has to do means this EMF has to see that it should not allow that North Pole to come closer to this. As that stupid fellow is coming closer to this coil, the flux linking with this coil are changing and EMF has induced. Now this EMF should say, no, 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 you cannot come closer to me. As you are coming closer to me, the flux linkages with me are changing. Due to that, an EMF is induced. But the sad thing is EMF is an electrical quantity here. but whereas the magnetic flux lines are your magnetic quantities. So they cannot, electrical quantity cannot directly oppose the magnetic quantity. Then how? Means if circuit is closed, then that induced EMF has to circulate a current. Then you can see this is a conductor AB, and this conductor is placed under a magnetic field. So that conductor has to experience a force. And what should be the role of that force? Means that force, that conductor should not allow that north pole to come closer to that coil. Why? Because this force is due to the current, and this current is due to the EMF, and this EMF is due to the changes in flux linkages, and this changes is due to that pole which is coming closer to that. So if this force stops the pole not to come closer to that, then the changes become zero, EMF becomes zero, the current becomes zero, the force becomes zero. So if it has to stop, means what should be the pole that has to be formed here? A north pole. Why? Because what is the pole that is coming there? North pole. So unless and until there is a north pole, there is no repulsion there. So when there is no repulsion, so that pole cannot come here. So for this north pole, so the flux lines has to come out. So when the flux lines has to come out, you know this right hand thumb rule. We can use this right hand thumb rule in either way. What is that? If you want to know the direction of flux lines, if you know the current direction, you can know the direction of flux lines. So if the direction of current is upward, the direction of flux lines will be like this. And if you are having the magnetic flux lines like this, then the direction of current will be like this. Then you can see reverse you can use. So here the magnetic flux lines should come out. In this case, it has to come out. So from coil, the magnetic flux lines has to come out. That means in which direction the current has to flow, the direction of current should be from B to A. So if it is B to A, the flux lines will be coming out. So that EMF will circulate a current in such a way that the current has to flow from B to A. When the current is flowing from B to A, then the magnetic field lines will come out and they will opposite north pole, and the north pole will not come closer to that. So this is one way of defining this statement. In other way, how I'll define means, see, initially how many flux lines are traveling through that? There are no flux lines. Now because of this north pole, say some 5 flux lines are traveling. 5 flux lines are traveling. So these are the flux lines due to this pole, north pole. Pole. Now, what that current which is circulating should do means it has to see that the flux line should become zero. So if the flux line should become zero, means what should be the direction of flux lines? The direction like this. Direction of this flux line should be like this. This is due to this coil. If the magnetic flux lines has to cancel that flux lines, so in which direction the current to flow, has to flow? So two ways I can tell. Two ways. What is that? Initially the flux lines are zero, but when the magnet is coming closer to that, the flux lines are increasing. But the Lenz's law says that no. The initial flux lines were zero. The flux line should remain zero only. So how many flux lines are traveling now? Say 5 flux lines are traveling. Then that flux lines which are traveling will induces an EMF. That EMF will circulate a current. That current carrying coil will produces one more flux. This flux will oppose that flux, so that the flux lines or the flux remains zero. You can see this flux cancel, this flux cancel, this flux cancel, this cancel. Again that flux becomes zero, the changes become zero, the EMF can become zero. So it is something like rejection process. So the increase in flux is being rejected. So you cannot increase, please rejected. So it is rejected here. So the flux lines are being rejected, flowing through that coil. Why? Because the initial flux lines are zero. Is this point clear? All of you explain me. Raise the hands. Is it clear? Right. Done. So any example? Yeah, I told you that I'll give. Right? Don't worry, I'll give. Now I'll take you the other case. You the other case. What is that other case means? In this case, this is a coil. Again, I'll consider the same coil. This is a coil. This is the coil. Initially, the switch is open. So here it is A. This is B. Now this time, this North Pole is very close and this is for long time. This North Pole is very closer to that coil and it is for long time it is there. Then here the flux linkages are maximum. As this coil is for long, this magnet is for long time, the number of flux lines passing through this are maximum. They are maximum. So they are maximum. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Right. Now what I'll try to do means, I'll try to move this magnet back. When I try to move this magnet back, then what happens to the number of flux lines through that coil start decreasing. As the magnet is moving away, the number of flux lines starts decreasing. So instead of using the terminology decreasing, I'll say the flux lines are changing. So due to the changes, what is induced here? An EMF is induced here. So here in this case, the EMF will be due to the changes, right? Here the coil is not moving. So I'm trying to explain that, right? Right. No. Fine. So is it clear? Right. Now when that magnet I'm trying to move back, when I'm trying to move this magnet back, then what happened? The flux linkages with that coil are changing. Due to the changes, what is induced? EMF is induced. This EMF says, are you stupid fellow? A North Pole, you are with me and you are very close to me. When you are close to me, the flux lines are maximum and you are there for long time. So the flux linkages are maximum, there is no change. But when you started moving away from me, the flux lines are changing. So as the flux lines are changing and EMF is induced, no, this coil should not have an EMF. So you should not go back. As you are going back, the flux lines are changing. No, you cannot go back. Please come back. Please come back. If you are coming back, so the flux lines will be again maximum, right? So if you want to come back, what should happen? So this EMF should produce as a current. So the current carrying coil should produce as a force, and this force should see that that North Pole is coming back. When the North Pole is coming back, the flux lines will be again maximum. If the North Pole has to come back, means what should be the pole here? So there has to be a South Pole formed here. So if the South Pole has to be formed here, then you can see the direction of flux line should be into. If the direction of flux line should be into means, if the flux line should be into means, what should be the direction of current in this conductor? The direction of conductor current will be from A to B. If it is A to B, so the direction of current is A to B, the flux lines will be upward, and you can see the North Pole will be pulled back so that the flux lines again remains maximum. In other way, can I say, as the magnet is going back, let me consider two flux lines have reduced. But how many flux lines should remain? 5 flux lines should remain. So that current carrying coil will produce as one more field, and that field will try to compensate the reduction. So how many flux lines are now here? 5 flux lines are here. So whatever the reduction we have due to the moving away of that North Pole, flux lines reduce, so that will be produced or that will be compensated by that current carrying coil, so that the total flux remains again maximum, right? So in the first case, the flux linkages was 0. As the magnet is coming closer, it is saying no, you cannot come, please reject. In the second case, the flux lines are maximum. As it is moving away, no, you cannot move back, please come back. So it is something exactly opposite is happening. First time it is rejecting. No, you cannot increase the magnetic flux lines, you go back. In the second case, it is regretting. No, it is maximum, we cannot go back, please come back, please come back. So please come back. So it is something like regretting. So I'm using the terminology regression. So here can you see, so this is the direction of field, magnetic field, it is upward, so this is downwards. But here you can see the magnetic field is upwards, even the flux due to that current carrying coil is also upward. So in the second case it is aiding, in the first case it is opposite. So the same thing will happen even in case your normal life. What is that? I'll tell you. So people are eager to know, right? So what is that, sir, in normal life, right? We'll see. I'll tell you. See, if any new friend is approaching you, then what you say? No, you cannot be my friend, please get out, get lost. You cannot be my friend, please move away from this. You'll reject that fellow, right? But once you become the thickest friends, Then if that fellow is moving away, then you say, no, 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 you cannot go back. Please come back. So you'll try to put all efforts to bring that friend back. So you'll be regretting here. But if that fellow still goes, then you'll go for depress. So it is something like. So in every life, it is called as lens law. So initially you make friendship, you become thick friend. Once he leave, then you regret. So initially you are rejecting. After you become thick friend, you are regretting. So here also the same logic. If the initial flux lines are zero, so it will not allow the flux lines to increase. The Lenz law will say, so if the initial flux lines are zero, if the flux lines are trying to increase, so there is an EMF, that EMF will circulate a current, so that current will produce as one more flux, so this flux will oppose that increase in flux. Why? Because that flux should see that the initial EMF should be again zero. In the second case, if the flux lines are maximum, if the flux lines are start decreasing, an EMF will be induced, that EMF will circulate a current and that current will produce as a flux. So that flux will try to aid, or the number of flux lines which are reduced will be compensated here. So whatever is happening, exactly the reverse will happen in Lenz law. I hope this point is clear. All of you confirm me, raise the hands. Right. So this is something about Lenz law. Baba, see, remember, so we'll be making use of this Lenz law in detail in the coming days, right? So the points just noted. If you open any textbook, so there will be some paragraph given on this Lenz law. You know what is the statement given? So if the initial flux lines are zero, if the flux linkages with that coil are changing, so due to the changes in flux linkages, an EMF will be induced in that coil, and that EMF should produce a current such a way that that current carrying coil will produce as a field to oppose the increase. If the flux lines are increasing, it will oppose the increase. If the flux lines are decreasing, it will oppose the increase, means it will try to produce a flux to add the decrease. So whatever it is happening, it is doing in an opposite way. So this is something about your Lenz law, right? So these are the things which are very, very essential to understand the basics of your machines. I'll just repeat once again. So first point to be noted, first law to be noted is your Faraday's law. What is that Faraday's law? If the flux linkages with the coil changes, due to the changes in flux linkages, an EMF will be induced. By how many ways the flux linkages with a coil changes means two ways. What is that? First way is the field is stationary and the coil is moving. In the second case is the coil is stationary, the flux magnitude is varying. In the first case, we call it as flux cut. In the second case, we call it as changes in flux linkages. Next one is, if you want to know the direction of induced EMF, then you need to call upon either Lenz law or you need to call upon Fleming's right hand rule. Fleming's right hand rule we use for dynamical induced EMF. This Lenz law we use for statical induced EMF. Similarly, what is that motor law states? That means if a current carrying conductor is placed under a magnetic field, so that conductor will experience as a force. Why we have seen in which direction it will rotate means that is given by Fleming's left hand rule. So we have seen what is called as Lenz law finally. So these are some basics which are very, very essential, which should be understood clearly. Next one is induction machine, right? So before we discuss, let me write some point. Induction machines. Let me change this. Right. Induction machines. Right. So here an induction machine is basically a rotating machine. See, if you recall so-called as BTech, your team might have told you the classification of machines. So electrical machines may be classified into static devices and rotating machine. Static devices means you can see there are no rotating parts inside. Rotating machine means at least one part should be rotating. So in which category this induction machine comes means, so this induction machine comes under the category of rotating machines. So whenever we are talking about rotating machines, please remember that we can convert one form of energy into another form. That means we can convert a mechanical energy into electrical energy, or electrical energy into mechanical energy. So using these induction machines, we can convert one form of energy into another form, either electrical to mechanical or mechanical to electrical. So tomorrow, if anyone questions you, Are Baba, is it possible to convert electrical to mechanical and mechanical to electrical using induction machine? Means yes, right? So can I say the first point is it is a rotating machine. It is a rotating machine. A rotating machine used to convert mechanical energy into electrical energy. In this you can write induction generator, induction generator, electrical energy into mechanical energy, we call it as induction motor. Induction motor. See, whenever we are talking about energy conversion, so I can name these machines as electromechanical energy conversion. So electromechanical means we can change the electrical form into mechanical form, or mechanical form into electrical form. So we can convert, right? So one form into another form. So these are called as electromechanical energy conversion devices or machines. Devices. So the first point to be noted is under which category this induction machine comes, means it comes under the rotating machines, right? So definitely if you look into these induction machines, you can see a rotating part. The second point to be noted here is there is no separate construction for motors and there is no separate construction for generators. Any manufacturer across the globe, they will construct only one machine, induction machine. So that machine can be used either for motor or for generator. How, sir? Why only one construction, right? If you recall Faraday's law, the Faraday's law states that if a conductor is moved under a magnetic field, an EMF is induced, right? So what is the mathematical form of Faraday's law? Means if I'm having a conductor of finite length L, and if this conductor is moved with a velocity V under a magnetic field B, an EMF will be induced in that conductors, right? So what happened? Right, let me check. Magnitude is according to how much? It depends upon the intensity of the field, right? Right. See, but whereas in case of your so-called as Lorentz law, if a current carrying conductor is placed under a magnetic field, so I'm having a conductor, and if this conductor a current, and if it is placed under a magnetic experiences a force. So if you look this Faraday's law, the mathematical common things are B. So here also Lorentz law, the common things are B. So what do you mean by that? See, why I'm talking about only one machine. See, I'll be having a magnet magnet, a north pole, and I'm having a magnetic field. Magnetic field. The first condition is done, magnetic field. The second condition is I'm having a conductor of finite length L. I'm having a conductor of finite length L. This is a conductor of finite length L. Now, if I want to use this machine as a generator, then what I need to do? So this conductor should be connected to some external prime mover, and using this prime mover torque, I need to move that conductor. When I move that conductor will cut the magnetic flux lines. Whenever the conductor cuts the magnetic flux line, an EMF is induced, and that EMF is used to drive the current into the load if you connect a load. So in this case, this machine is acting as a generator. Why? Because using that mechanical energy, we are moving that conductor. So whenever you are moving that conductor, so the conductor is cutting the magnetic flux lines. So whenever the conductor is cutting the magnetic flux lines, an EMF is induced. So we are converting this electrical power to mechanical to electrical power. But instead of moving, if I pass a current in this, if I pass a current, instead of coupling to a prime mover, I'll give it to a source. So if I pass a current, then you can see that current carrying conductor will experience a force, and that conductor will start moving here. So what is the thing? In case of a generator, we need to see that the conductor should be moved in a magnetic field. So if I want to move the conductor in a magnetic field, I need a mechanical energy. So that mechanical energy is used to move the conductor. But whereas in case of motors, so that conductor should carry a current. I have to take an electrical power and I have to pass a current to that conductor, so that conductor will experience as a force. So you can see construction wise, we don't have separate construction for motors and generators. Why? Because the common parameters, the common things which are required is magnetism and conductor. In case of generator, so the conductor should be moved. For that, we need a mechanical energy. In case of motor, the conductor should carry a current. For that, we need to have some electrical source. So tomorrow, if anyone questions you, do we have a separate construction for motor and generator? No. Why? Because the generator works on Faraday's law, BLV. The motor works on Lorentz law, BIL. In both the cases, B and L are same. In case of generator, we have to move the conductor. In case of motor, we have to pass the current. So can I say there is no separate construction for motor and generator, right? I'll write a next point. Right. There is, see, someone wrote break. I'll give after this. Just give me 1 minute time. Just 5-10 minutes, we'll go for a break. Right. There is no separate construction for generator and motor. There is only one construction called machine construction. A machine construction. Machine construction. Can I write if the input to the machine is mechanical in form, the machine act as a generator. So whenever I'm talking mechanical means we are moving the conductor. So whenever the conductors are moved, the flux lines are cutting the conductors. Then what is induced? EMF. So the machine acts as a generator. Second point is, if the input to the machine is electrical in form, electrical inform the machine acts as a motor. So if anyone questions you, are do we have separate construction for motor and generator? No. Why? Because in case of generator, the conductor should be moved. For that we need, in case of generator, the conductor should be moved. For that we need a prime mover. In case of motors, the conductor should carry current. For that we need some electrical power, right? This is the second point, right? The third point is, this is the second point. The third point is, so here induction machine operates in two modes. By looking into the rotor speed, we can decide whether the machine is in motoring mode or a generating mode, right? So we'll see all these things, don't worry. Induction machine operates in two modes. One is if N generally we use N for speed, NR means rotor speed. If NR is less than NS, then it will act as a motor. And if NR is greater than NS, it will act as a generator. So in the coming days, nearly some 2 to 3 hours, not 3, 3 to 4 hours will spend. Why in case of motors, the rotor speed will be always less than NS, and why in case of generators, the rotor should be more than NS. What is the reason for that? We'll see, right? We'll discuss that, don't worry. Here NR is a rotor speed, NS is the synchronous speed, right? Next and very important point is, if the rotors, you may have a doubt, what is that synchronous speed? Just next I'll discuss that. If NR is equal to NS, that means if the rotor speed and the field speed both are same, then this machine neither it will act as a generator or motor, and hence these machines is also called as asynchronous machine. So please remember, asynchronous means a single word, asynchronous machines. Why? Because motoring is possible with the speeds less than NS, generation is possible with the speeds greater than NS. So that's the reason it is called as asynchronous. So tomorrow in your examination, if the name asynchronous motor is given, don't come and fight here. It is other name for your induction. So just as of now, I'm leaving this concept. Why in case of motor, the rotor speed will be less than NS, and why in case of generator, the rotor speed has to be greater than NS, and why if the rotor speed and the field speed both are same, motor or generation is not possible. We'll see everything in detail. Just give me some 5-6 hours. After that, I'll be discussing. So these are the points to be noted, right? Once again, if anyone questions you, are an induction machine is a rotating machine or a static device, then you are supposed to answer it is a rotating machine. So whenever we are talking about rotating machines, so can we convert one form into another form? Yes, that means we can convert either electrical energy into mechanical energy or mechanical energy into electrical energy. We can convert. The second one is, a manufacturer will not construct a motor separately or a generator separately. So there is only one construction called as a machine construction. Why? Because the common thing are magnetic field and conductors. So if we want to have a generating action, so that conductors or those coils should be moved. For that, we need a prime mover. If I want to use that machine as a motor, so that conductor should carry current, we need some electrical power. So there is no separate construction for motor and generator. There is only one construction. So if you are giving mechanical energy, so we are moving the coils, the conductors are cutting the field, and EMF is induced, so that is acting as a generator. If you are using some electrical power, or if you are giving current, then the current carrying conductor will experience as a force, then it will produce some mechanical force. So electrical is converted into mechanical. So here in this case of induction motor, if the rotor speed is less than ns, it is a motoring action. If the rotor speed is greater than ns, it is a generating action. But if the rotor speed and the field speeds both are same, neither motoring or generation. The next one is features. We'll discuss after the break. So in these features, we are going to discuss very, very important points. What are those important points? See, it may be your transformer, it may be your DC machines, it may be your synchronous machines, or it may be your induction machines. We need two magnetic fields. Two magnetic fields are required, and the relative speed between the two magnetic fields has to be zero. Unless until the relative speed between the two magnetic field is zero, neither generation is possible, neither motoring is possible, neither in case of your transformer, electrical power is transferred. Nothing is possible. So very compulsorily, if you want to have motoring, means converting electrical to mechanical, if you want to have generation, converting mechanical to electrical, if you want to have power transfer in case of transformer from primary to secondary, in all cases in the same magnetic circuit, how many magnetic fields are required? Two magnetic fields are required. If you are not having two magnetic field, there is no question of power conversion, there is no question of power transfer. Nothing will be done. Why? We'll see, right? We'll see. So any doubt? So 1 second. Summarizing. Again, black background. Sir, we are going to learn about generators and motor. Of course. See, it is not like generators we are going to discuss in detail. 95% discussion will be only, not 95, 97% discussion will be on motors. 3 to 4% will be on generators according to your syllabus. Nothing more than. Oh, charging. I'll charge. Thank you, Baba. Okay. Thank you. See. So you'll see Manjunath. So how the construction will be same, sir, for generators? I didn't understand that. We'll see that. Neither motor nor generator means what, sir? So it will not act. That means what is the meaning of motoring? I'll tell you, anonymous attendee. What is the meaning of motor means? You have to give electrical power. It has to produce mechanical power. It will not give any mechanical power. What is the generation means? When you are giving some mechanical energy, so there should be some voltage across the conductor. There is no voltage. So when the rotor speed is equal to synchronous, so neither voltage is there nor torque will be there. So both will be zero, right? Yeah, I'm giving break. So break has not started. See, what is the relative speed? All this we'll discuss, Baba, don't worry. So induction generators will be used in your wind turbines. That we'll discuss. See, today is the basics class, don't worry. Right. So can you please explain asynchronous? See, Baba, why the name asynchronous has come means we can see motoring is possible when the rotor speed is less than ns. Generation is possible when the speed is greater than ns. As motoring and generations are possible with the speeds other than ns, so that is the reason it is called as asynchronous. Asynchronous means other than synchronous speed only, either motoring or generation will be possible. Sir, if it is neither a motor nor generation, for what purpose? No purpose. So there is no motoring or generation. I mean to say that if you want to operate it as a motor, so the speed will be less than. If you want to operate it as a generator, the speed will be, has to be greater than. Please remember that. No, it is not possible. Is it possible? See, Baba, give me time. So all this will get it in your working principle. NR is equal to NS. There is no chance that the rotor speed can be equal to synchronous speed. See, Usha, sir, what is the principle of a induction machine? It is the same principle as your other machines. That is, if you are talking about motors, Lorentz law. If you are talking about generators, Faraday's law. Right. So we'll discuss. So, sir, in synchronous machine, it is synchronous speed. Yes, the rotor speed is always equal to synchronous. That is the reason it is called a synchronous machine. Yes, we can use the same motor as a generator also. So in case of regenerative braking, the same motor is feeding the power to the source. Please remember. Yeah. Sir, Salman Khan, your introduction, I'll give, don't worry. So let me finish this. Right. Anyhow, so this is some, sir, it is similar to transformer. Just give me some time, Baba. I'll explain. It is very similar to a transformer only, right? So these are one request to all. See, whatever the questions you have raised, they are all from your working principle, right? So you can see I'll spend nearly some 3 to 4 hours on the working principle. So whatever the questions you have raised and now you'll get the answers for all. Some questions is, sir, why the name asynchronous? The speed will be always less than. Why it will be always less than? We'll see. Sir, is the rotor speed is equal to synchronous speed? No. Why, sir? We'll see. Why the generation will take place if the rotor speed is greater than synchronous? We'll see all this. Just give me some time, right? So we'll take some break. So it is 20 minutes break. After that, I'll come back, right? Fine. Right. So I'm back. So now let us discuss some features, right? So can you tell me, all of you raise your hands once? Right. So I'll be discussing features. So the first feature is it works on mutual induction principle, just like your transformers. On what basis this mutual induction principle name has come, right? We'll see. If you recall the basic motor law, what is that basic motor law? F is equal to BIL. So by looking this equation, one can say that if I want to have force motoring, what are required? B, magnetism. I need a conductor of finite length L, and through that I need to pass some current. I need to pass some current. So if the current carrying conductors are placed under a magnetic field, so that conductor will experience as a force. So in case of an induction motor, how these conditions are being fulfilled means we'll see one by one. So I'll be having a stationary part called as a stator, and in the stator we'll be placing a three-phase winding. Three-phase winding. Three-phase winding. And whenever I pass a three-phase currents, then immediately we'll have a magnetic poles. We'll see this in the coming session. Whenever we are having a magnetic poles, we'll having magnetic flux lines. And what is the nature of these poles? Means they are rotating poles. As the poles are rotating, the flux also rotate and the magnetic field lines are also rotating. So the first condition is over. Don't ask as of now, sir, how the poles are rotating. Everything we'll see in detail in complete discussion in the coming sessions. Don't worry. The second condition is I need a conductor of finite length L. So where we are placing those conductors of finite length L means this is a rotor. On the rotors we'll make slots, and in the slots we place the conductors. So these are the conductors of finite length L. What is the last condition that need to be satisfied means through that conductor I need to pass a current. So in order to pass a current, I'm not using any separate source, or we are not using any separate source. So whatever the current that is induced will be due to induction. How means these magnetic field lines as they are rotating, they cut the conductors. As a result, what is induced? EMF. As the rotor bars are closed on either side, we'll see all these things in the coming days. Don't worry. What circulates? Current. So if these are the poles, these are the conductors. So as these poles are rotating, they are cutting the conductors EMF. As the conductors are closed, due to that closed current, so the current carrying conductors are placed under magnetic field, and hence these conductors will experience as a force. So here, whatever the current that flows in the conductors, that is I, is due to induction principle. That current we call it as a induced current. That current we call it as a induced current. As that current is called as as that current is a induced current, as this current is due to induction, so this motor works on induction principle. But whereas in case of DC motor, the same logic, right? In case of DC motor, the first condition is B. So how that first condition is satisfied in case of DC motors? The first condition is magnetic field. So we'll be having magnetic field, and we'll be having the armature, and we'll be having the armature conductors, and the other side of the armature conductors are brought out, and through this we are passing a current. So these current carrying conductors are placed under a magnetic field, and these conductors will experience a force. You can see the same concept, F is equal to BIL. So here this I is due to conduction. Using an external source, we are supplying the current into that conductor. As the current carrying conductors are placed under a magnetic field, those conductors are experiencing the force. You can see the difference between the rotor currents in induction motor, the armature currents in case of DC motor. In case of induction motor, that current is a induced current, but whereas in case of DC motor, that current will be a separate current, that is a conduction current. As this current is an induced current, as this due to the magnetic field lines are cutting the conductor, EMF, as the circuit is closed current, this current is induction principle. So that is the reason it is called as a induction motor. So can I say finally, this motor works on induction principle. So this motor works on induction principle just like a transformers, just like a transformer. Just like a transformer. So that is the reason it is called as a induction motor. So what is the other name we can give it for this motor means asynchronous motor. Why it is called as asynchronous motor? As the rotor speed is always less than the synchronous speed, as the rotor speed is always less than the synchronous speed, why we'll see, as it is possible, as motoring is possible with the speeds less than synchronous speed, it is called as synchronous motor. Why it is called as an induction motor means as those currents are due to induction principle, so that is called as induction motor. I hope you understood the difference between synchronous, less than synchronous, induction motor. I hope you understood that. Please confirm me, all of you. Confirm me. Right. So this is as induction motor. The second one is, this one we call it as a single excited machine. This one we call it as a single excited motor. What is called as a single excited? This is a very important concept. Single excited motor. Single excited motor. Just like transformers. What is called as a single excited? As I told you that for any motor, for any generator, or for any transformer, so how many magnetic fields are required? Two magnetic fields are required. And the relative speed between the two magnetic fields has to be 0. Why? We'll see, try to understand this. So first I'll try to explain the transformer concept, then I'll come back to here. See. So if I take a transformer here, this is one coil. This is another coil. You know that a transformer doesn't carry primary and secondary unless the source size is decided. So these are windings. When I'm trying to do excitation here, let the number of turns be N1 and the number of turns be N2. When I use excitation here, then this will draw some magnetizing current. So that magnetizing current into N1 will produce as one MMF. MMF will drive the flux, and this flux nature will be alternating. An alternating field will be passing in the core, and on the core will be having winding. As it is an alternating field, flux lines will be changing time, and with respect to the coils which are placed on that, the flux linkages will be changing. As a result, what is induced in both the windings and EMF will be induced. But you can see in the core there is only one field, there is only one flux. So because of this only one flux, there is no power transfer to that secondary. Now, when I connect a load here, then what circulate? Right. Sorry. So whenever I connect a load, what happened now? A current circulates. So because of the secondary current into N2, there is one more flux. We call it as phi 2. Right before that way. So this magnetizing current I mu is equal to the applied voltage by induced voltage. This is E1 by Z1. But whenever we connect a load here, what circulates? Current. So due to this current into N2, there is one flux, and this flux will oppose the mains. When this flux is opposing the main flux, then what happened to the flux in the core? Decreases. Why? Because the secondary flux is opposing. When the flux in the core decreases, what happened to this E1 decreases. When E1 decreases, what happened to this difference? V minus E1 increases. When it is increasing, some additional current is drawn from the source. So whenever that is increased, so V into I, so this power will increase. So where is that power going? Means that power is going to the secondary or to the load. So can I say like this? How that load will communicate to the source means, so whenever you are connecting a load, a current circulates in the secondary. That current will produce as a flux. This flux will be opposing the main field. Because of that, the flux in the core will decrease. Then E1 will decrease. V minus E1 will increase. The current drawn will increase. The power drawn will increase. Why? Because current is increasing. Power drawn will increase. Where is that power is going? That power is going to that secondary, or it is going to the load. So who is responsible for this power transfer? Means this secondary flux. How? Means that secondary flux is opposing the main field. Because of that, the flux in the core is decreasing and E1 is decreasing. So this E1 is the back EMF we call. This plays a vital role here. Because of the decrease in E1, by because the flux in the core is decreasing. E1 is decreasing, V minus E1 is increasing, current drawn is increasing, power drawn is increasing, and that power is going to the load, and that power is supplied to the load. So unless and until the secondary flux is there, there is no concept of power flow. For example, if I disconnect the load, what happened? I2 becomes 0, phi 2 becomes 0, opposition becomes 0, E1 and V will be almost the same, current drawn will be less, power drawn will be less, and that is going to the losses in the machine. So whatever that small power that is being drawn under no load is to compensate the losses, not to supply the load. But when you connect the load, current circulates. Because of that current, one more flux, and because of that flux, there is opposition. Because of that, the flux in the core will decrease, and EMF E1 will decrease, and V minus E1 will increase, current will increase, power will increase, the power will supply to the load. I hope you understood this. All of you raise the hands if you followed this. Right. So can I say if I want to have two fields, so how many electromagnets are required? Two electromagnets are required. This is one electromagnet. This is one electromagnet. What is an electromagnet? If you remember, an electromagnet is a core. On the core, winding, and through that winding, current. This core, this is one winding, and this is one current. Similarly, this is one core, this is one winding, but whatever the current that circulates to the secondary or the current that flows in the secondary is the induced current. So for that, how many sources are required or how many currents are required? There is only one current required. So that is the reason it is called as single excited machine. On what basis I can say it is a single excitation means you can just tell like this. For the transfer of power, we need two magnetic fields, and we are producing these two magnetic fields using two electromagnets. And to produce the magnetic field, we need two coils, two windings, and two currents. But whatever the current that flows in the secondary is not due to the supply current, it is due to that induced current, and that current is due to induction. As we are using only one source to supply the current, so that we call it as a single excited machine. Single excited means you are using only one source for both the currents. This current is supplied in this winding. Due to this field EMF, that current is due to that induction. So on this basis, we call it as single excited machines. So this is called as a single excited. Is this point clear? All of you confirm me? Is this point clear? Confirm me? Right. Right. Done. So this is something about single excited machine. So these are two features. So the coming features we are going to discuss basing on the working and basing on the performances, right? So these are the points to be understood as of now, right? So someone has texted, just give me some time. Anonymous attendee, sir, for my BTech, sir, also you thought mentioned. You are from which college, Baba? Then I tell you. So volume is good. So how it works on induction principle, already I explained that. Now my voice is clear, all of you confirm me. My network is clear, Baba. Right, done. Next concept is the concept of rotating magnetic fields. Rotating magnetic fields. So this is a very, very important concept. Rotating magnetic field. Right. Rotating magnetic fields. Particularly in case of induction motors, one has to understand clearly how a rotating magnetic field can be produced. Clearly, one has to understand this. First, what I will try to do means I'll try to explain what is called as rotating magnetic field and how we are trying to produce that rotating magnetic field in induction machine. One has to understand. See, what I will do means I'll consider a permanent magnet. Let it be North Pole and let it be South Pole here. And you know that the magnetic field lines will be originating from North Pole and terminating at a South Pole. And to complete the path, the same magnetic flux lines will be traveling from south to north, like this. So if anyone questions you, or nature of that magnetic field means it is a stationary magnetic field. Why I'm calling it as a stationary magnetic field means the poles are stationary, the magnetic flux lines are stationary, so it is a stationary magnetic field. It is a stationary magnetic field. Now what I will do means I'll take the same magnet, and I couple this magnet to some external prime mover, and using this external prime mover, I'll rotate this magnet. Whenever I rotate that magnet, whenever the magnetic poles rotate, the flux lines will also rotate, and the nature of this system will be a rotating magnetic field. So if anyone questions you as of now, or how to produce a rotating magnetic field, means you can answer like this. Take a permanent magnet, connect that permanent magnet to some external prime mover, and using that external prime mover, rotate the magnet. Whenever you are rotating the magnet, obviously the magnetic poles will rotate. Whenever the magnetic poles rotate, the flux around that will also rotate. So this is one way of producing rotating field. But fortunately or unfortunately, what is the main problem we are having with such type of rotating magnetic field means it is a uncontrolled uncontrolled magnetic field. What is the meaning of uncontrolled magnetic field? Means we are not having the control over the magnetic flux. When we are not having control over the magnetic flux, in case of generator, this B is uncontrolled, then E will be uncontrolled. E into I, that power is also uncontrolled. So that generated electrical power is also uncontrolled. In case of motors, F is equal to BIL. So if this B is uncontrolled, so this force will be uncontrolled. Force into perpendicular distance, torque will be uncontrolled. The mechanical output power is also uncontrolled. So if you are producing a rotating magnetic field with a permanent magnet, the nature of that magnetism is rotating, but it is a uncontrolled magnetism. Because of this uncontrolled magnetism, so the output electrical power is uncontrolled, the output mechanical power in case of a motors is uncontrolled. So that is the reason we don't use such type of rotating magnetic fields either in generators or motors. Why? Because we have an uncontrolled electrical power and uncontrolled mechanical power. Then how to have a controlled magnetic field? Control magnetic field. Control magnetic field. Magnetic field. So I told you that according to Ørsted, a current carrying conductor can produce as a magnetism. So what I will try to do means I'll take a conductor here, say length conductor, let me consider. And through this conductor I am passing a current. And I am considering a point P at a distance R. Then the intensity because of this means, so you might have studied, it is B is equal to, so instead of telling that, so it looks like I'll be teaching EMF, let it be. So it no one looks good, leave it. So if I consider a long conductor carrying a current, then we'll be having a magnetic field. But if I take a coil, so when compared to this, so it is under your EMF concept. That's the reason I'm not discussing. So if I'm having a coil, then in which case the magnetism will be more, means the magnetism will be more in this case. If I consider a point P at a distance of R, here the magnetic field intensity will be more compared to here the magnetic field intensity. So if anyone questions you, are compared to a long conductor carrying current, so which one will be having more magnetism? Means a circular coil, a circular coil. So that is the reason if you come across anywhere about electromagnet, we don't take a long conductor carrying current, so we take a coil carrying current. Why? Because when compared to a long conductor carrying current, a coil carrying current will be having more magnetism. So which one will be having more magnetism is a current carrying coil. The next one is I'm having a coil without core, say with N turns. I'm having a core, on the core I'll be having a coil. I'll be having a coil. So let the number of turns be N. So this current is I and this current is also I. So if my question is among these two, in which case the magnetism will be more, means you will answer the second case. The question is why in the second the magnetism will be more, means there is one theory, right? So there is one reason, there is one theory. What is that? Let me explain, right? So anonymous attendee. So what is that I need to explain? I explain everything. Right, correct. See Baba, from my side, everything is clear. See, this video is not freeze. You can see when I'm moving, the video is moving. So it is not freeze, right? Please. Right. Juna, sir, what happened to the final current and flux if we take a circular coil and twist it into two piles? See, it all depends upon your permeability, the number of turns. See, we are not discussing that much. My intention is to prove that. Right. So if anyone questions you, or when compared to the first case, why in second case the magnetism will be more, means I'll answer for that. What is that means? For that I need to discuss some material science. Please, Baba, one thing I want to let you know that, see, whatever we are discussing now, we are supposed to catch concept in the coming days. So these are the very basics, fundamental concept for machines. You are supposed to be followed this. It is not like something we have to learn here, leave it here. No, you have to carry this, right? We need this, remember. So why in the second case the mag will be more, means let me explain. See, those who are raising the hand, just wait for some time. So I'll give the scope, right? If you are having any questions, I'll answer. Just give me some time. After 8:30, we'll be having the doubt session. So all the doubts I'll clear. Just give me some time. Yes, please. My request is don't disturb. Let me see. I'm trying to tell you that I'll clarify your doubts, please. Right? If you're having any problem like strucking, that I'll check. That you can type it, please. So once I got this doubt clarification section, you can just type the questions. I'll give the time, please. Right. In the second case, why the magnetism will be more, means I have to discuss something about material science. Material science. So it looks like material science is part of electrical engineering. But remember, material science is part of electrical engineering. So very compulsorily we have to know the science about that material, right? We'll see. Right, it is moving, right? Done. So what is that material science means? See, if I consider any magnetic material, ferrous material, ferrous material, ferrous material. In this ferrous material, we'll be having small molecular magnets. So we call it as dipoles. Small molecular magnets we have, like this. So every time I cannot take. So we'll have small molecular magnets. Molecular magnets. So these are called as molecular magnets. The meaning of molecular magnet, call this one as a north pole, let us south pole. Like this, we'll be having poles. So small magnets, these are molecular magnets. So when there is no magnetism, or when this material is not subjected to any magnetism, so all these dipoles will be randomly oriented. These dipoles are randomly oriented. Randomly oriented. As these are randomly oriented, the magnetism coming out of this material is zero. As the magnetism coming this material is zero, it is called as a non-magnet. What do you mean by this, sir? Why it is called as a non-magnet, sir? See, I consider this one as a iron pen. Iron pen. If I take another iron pen, then if I place these two iron pens side by side, so there is no either attraction or repulsion. It is a magnetic material, but it is a non-magnet. Why it is a non-magnet means whatever the dipoles we have inside, all the dipoles will be randomly. There is no magnetism coming out of that magnetic material. Now what I will try to do is, I'll take the same magnetic material. Same the magnetic material, and closer to this, I'll try to bring a north pole here. When I try to bring a north pole here, poles which are randomly oriented. So these are the dipoles. So these are called as tiny magnets. Or molecular magnets. Molecular magnets. So what is the technical name to this means? These are as magnetic dipoles or magnetic domains. Domain, right? So these are randomly oriented and there is no magnetism. Whenever I try to bring a north pole to that magnetic material, what happens means all the dipoles which are randomly oriented will start aligning. How they will align means, as this is a north pole, so south pole will be coming here. So these dipoles will be aligned like this. South pole will be aligned like this. And during the process of this alignment, what happen means all the internal poles will be cancelled. So here, this north and south will get cancelled, and here this north and south will get cancelled. Here this north and south will get cancelled. Here this will get cancelled, and you can see this south pole will be left uncancelled, and this north pole will be left uncancelled. So like this, a south pole is formed here. Like this, a north pole is formed here. As soon as this south pole is formed here, so this will attract here. When that is attract, so the magnetic flux lines which are coming from that north pole will try to travel to that aligned dipoles. Like this, the magnetic flux lines will be traveling. If it was a non-magnet, now it is acting as a magnet. Why it is acting as a magnet means it is carrying the magnetic flux lines. As it is carrying the magnetic flux, it is acting as a magnet. So that is the reason I think in your school days, when you try to bring a magnet closer to some iron fillings, you can see those iron fillings will try to attract. As they are attracting, unless and until the opposite poles are formed on that, they will not attract. Why? Because the law of magnetism will says that like poles will repel, unlike poles will get attracted. So unless and until those iron fillings are acting as a magnet, they will not attract. So those iron fillings are acting as a magnet. So here also this core, this iron which was acting as a non-magnet, it is acting as a magnet now. So can I say here magnetic poles are formed now. Magnetic poles are formed now. Magnetic poles are formed. And such formation of poles we call it as induced poles. Induced poles. Induced poles. So tomorrow I'll be making use of the same terminology, induced poles. So whenever I'm using this terminal induced poles, then you have to imagine like this. Oh, there is a core, and this core is brought closer to a magnet, and because of the magnetism produced by that magnet, all the dipoles are aligned inside, and because of that, the internal poles are being cancelled and extreme poles are uncancelled, and this core is acting as a magnet now. Such formations we call it as electromagnets. Sorry, the such formation we call it as induced poles. Induced poles. So this is one type of induced pole. But what is the main problem we are having with this means, say, if I am having a room size core, in this room size core, say there are lakhs of dipoles inside. But if I try to bring a small magnet closer to this room size core, only some part of the dipoles will get aligned. All the dipoles will be left unaligned. That means the magnetism of that core is not fully utilized. Fully utilized. So for that reason, what I'll try to do means, instead of bringing pole to that, what I'll try to do means I'll try to take the same core. Now on the core, what I'll try to do means I'll try to place a coil. Coil, and through that coil I'll pass a current. And you know that current carrying coil will produces magnetism according to Oersted. So whatever the magnetism that current carrying coil is producing, it will try to align all the dipoles inside. As a result, a north pole is formed here, a south pole is formed here. So like that, magnetic poles are formed here. So such a type of pole formation we call it as electromagnets. 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 Why the name electromagnet has come means using electricity we are producing magnetic poles and magnets. So we call it as electromagnet, right? So if anyone questions you why in the second case the magnetism is more means, so can I say in the first case the magnetism is only due to the current carrying coil, but in the second case the magnetism is due to the current carrying coil and also the core which is acting as a magnet now. So how many magnetisms are there now? Two magnetism. One is a current carrying coil. The other one is the core which is acting as a magnet. So in the second case, the magnetism will be more. So that is the reason if you want to produce a magnetism artificially, we are not supposed to take a air core inductor or air core coil. We are supposed to have a iron core inductor or iron core coil. Why? Because in that case, that core is also acting as a magnet. The total magnetism coming out of the second case will be more compared to the first case, and hence the magnetism will be more in the second case. Is this point clear? Confirm me, all of you. Right. So here what I will do means, so why the name electromagnet has come. So as we are able to produce magnetism using electricity, using a current carrying coil, we are producing magnetic field. It is the reason electromagnet. Using electricity, we are producing magnetic field. Now what I will do means, I'll design one electromagnet here. On this, I'll place a coil, and through this coil, I'll be passing a current. So this is a north pole, this is a south pole. You can see the magnetic poles are formed. And what I'll try to do means, I'll try to connect this magnet to some external prime mover. Using this external prime mover, I'll try to rotate the magnetic poles. When I try to rotate the magnetic poles, the magnetism will be rotating around this. So this is the second type of rotating magnetic field. So here, by controlling the magnitude of current, we can control the field strength. So whenever the field strength is controlled, then we can have a controlled voltage. So whenever we are having a controlled voltage, we can have a controlled electrical power. Similarly, we can have a controlled torque, then we can have a controlled output mechanical power. So this is the second way to produce a rotating magnetic field. So if anyone questions you as of now, Are, can you please tell me by how many ways we can produce a rotating magnetic field means? You can answer two ways. What are those two ways? One is take a permanent magnet, connect that permanent magnet to some external prime mover, and using that external prime mover, you rotate the magnet. Whenever you rotate the magnet, then obviously the magnetic fields will be rotating and the flux around will also rotating. But what is the main problem we are having with this rotating magnetic field means it is uncontrolled. Because of this uncontrolled field, the output electrical power will be uncontrolled, the output mechanical power will be uncontrolled. So if you want to have a control electrical control mechanical power, we are designing a electromagnet. Take a core, on the core place a winding, and through that winding you pass a current and try to produce a field. Like that we are able to produce a rotating magnetic field. But whatever the rotating magnetic field we are trying to discuss now, in case of induction motor, we are not rotating the core, we are not rotating the winding. So here the core is stationary, the windings are stationary, but the poles which are formed inside are rotating. Now we are going to see how to produce a rotating magnetic field with a stationary core and a stationary winding. So in case of an induction motor, whatever the rotating magnetic field we have, it is not due to a rotating core or a rotating winding. The core is stationary, the windings are stationary, but the field which is used will be rotating. Now let us see how to produce a rotating magnetic field with a stationary core and stationary winding. So the next important is, so if anyone questions you tomorrow, or in case of an induction motor, the field will be rotating, but the core is stationary or rotating. The core is stationary. Now we'll see how to produce a rotating magnetic field with stationary core, right? So now rotating magnetic field with stationary core and stationary winding. Stationary winding. Stationary winding. So if I want to explain this, I'll ask some questions. Please see. What is an electric circuit? Please see, all these are linked questions. What is an electric circuit? So an electric is one along which a current flows, right? So I'll consider an electric circuit with a resistor and a source. So if I want to have current, I need the driving force. Driving force. What is the driving force for the current? EMF. Unless and until I connect a source, so there is no current flowing through that circuit. So what are the various sources we are having for EMF? I'm having a battery, right? So if I connect a battery for this resistor, so it can supply the current for some finite interval of time. So that battery cannot supply the current infinite time. It supplies the current only for finite time. You take a mobile. So in this mobile, there is one battery, right? So that battery can supply the current only for some finite time. So that is the reason we can see the units of batteries ampere hours. So this battery can supply the current only for this amount of time. It is ampere hours. But if I want to have a current for infinite time, so the battery cannot supply the current for infinite time. In that case, what I need to do means I have to move a coil. Coil is moved in magnetic field. When coil is moved in magnetic field, then the flux linkages with that coil will be changing, and due to the changes, an EMF is induced. So how we are getting a current here means long away or from kilometers away. So the coils are moved under a magnetic field, that is in generators, the coils are moved under a magnetic field. So voltage is induced, that voltage is connected via the transmission line, and here we are taking that voltage to circulate a current and to get the power. So if the generator is rotating continuously, so that EMF will be continuous. When that EMF is continuous, the current what we are getting to the load will be continuous. So we'll get a continuous current, right? So if anyone questions you, what is an electric circuit? An electric circuit is nothing but along which a current flows. Or if you want to have a current, what you require? The driving force. What is the driving force for that current? An EMF. What are the various sources of EMF? One is the battery. The other one is a coil moved under a magnetic field. What is the main problem with a battery? The battery can supply the current only for finite time. But if you want to have a current for infinite time, then you should move the coil like infinite. It has to be continuously moved. Then we can have a continuous current. We can have a continuous power. Is this point clear? Confirm me. Is this point clear? Confirm. Right. So one more thing. If this is a DC source, the current is also DC. So can I say the nature of that current depends upon the nature of EMF. If it is a AC source, the nature of current will be AC. Similarly, very similarly, if I want to have flux in a magnetic circuit, so what is the definition for magnetic circuit means? Magnetic circuit is nothing but along which the magnetic flux lines will travel. Just like electric current means it is the path along which an electric current flows, magnetic circuit means it is the path along which the magnetic flux lines will flow. So what is the driving force for this magnetic flux? Driving force for the magnetic flux? EMF. EMF. What is the definition for MMF? Magnetomotive force. Just like electromotive force, the force which is responsible for moving the electrons. So magnetomotive force is the flux and the force which is responsible to align all the dipoles. So what are the various sources of MMF? One is a permanent magnet. So what is a permanent magnet means? If you just go back to this concept, so if I'm having a permanent magnet, if I bring this permanent magnet closer to this core, you can see the flux lines are traveling through this circuit. So who is responsible for aligning all the dipoles? When all the dipoles are been aligned, the flux lines are traveling through that part. So here, who is responsible for aligning those dipoles means a permanent magnet. So what is the first source for that MMF means a permanent magnet. What is the other source means the current carrying coil. What is the main problem we are having with the permanent magnet means it can align only the partial dipoles, but not all dipoles. So if I want to align all the dipoles, I need a current carrying coil. So what is the other source of this MMF means a current carrying coil. Current carrying coil. Current carrying coil. Right. So once again, if I want to have flux in a magnetic circuit, what is the driving force for the flux? It is nothing but MMF. So what are the various sources of MMF we are having means one is a permanent magnet, the other one is a current carrying coil, right? So just like the current depends upon the nature of EMF, the flux depends upon the nature of MMF. If MMF is a if MMF is a rotating MMF, the field is also rotating. What do you mean by that? Here, let me give a point here. The nature of flux depends on nature of MMF. If the nature of MMF is stationary, field is stationary, if it is rotating, the field is rotating. Field is rotating. Magnetic field is also rotating, right? So if I want to produce a rotating field, I need a rotating MMF. If I want to have a MMF, I need a current carrying coil. So initially what I'll try to do means I'll try to take a stationary core, and in that stationary core I try to place 3 windings, and through the 3 windings passing 3 currents. So when I pass those 3 currents into 3 windings, I'll be having 3 MMFs. How many MMFs I'll have? 3 MMFs. I'll find out the resultant of all those 3 MMFs. The resultant of all those 3 MMF is a rotating, then I can conclude that with that we can get a rotating magnetic field, right? So once again, if anyone questions and through that network, I need to pass a current. If I want to pass a current, what is that I need to connect to that network means the driving source. What is the driving source? An EMF. If you are connecting a EMF across that network, then that EMF will drive the currents into the branches. So what are the various sources we are having for that EMF means you can connect a battery. That battery can feed the currents in all the branches, but it is only for finite time. But if you want to supply the currents in all the branches continuously, then you need to connect that network to a generator terminals. Why? Because in generator terminals, those coils are continuously moved under the magnetic field. So the flux cuttings will be continuous, the EMF induced will be continuous, the current will be continuous, and the network will receive the current continuously. Yes, this how network will receive the current continuously while the generators are continuously moving there, right? Similarly, what is a magnetic circuit means I need to have magnetic field. So in order to have the magnetic field, what is the driving force for the magnetic field? It is a MMF. So what are the various sources of MMF? I can put a magnet or I can place a current carrying coil. So what is, I'll try to take 3 coils and I try to place 3 windings, that is 3 coils, and through the 3 coils I'll pass a 3 currents. So if I'm successful that if the 3 coils are producing a rotating MMF, then I'll get a rotating field. So initially we'll see how to produce a rotating magnetic field with a 3-phase and 3-phase current. So that is the reason those 3-phase windings and 3-phase current will act as a source of driving the field in the air gap. As this MMF is rotating, the field is also rotating. We'll see this in the next class. Now I'll spend time for question and answers. So most of you raising the hands as I promised you. So each and every question will be answered, right? Just give me some time. Let me just bring the earphones. I'll just connect to that. I'll come back. Just 2 minutes time. Right. So first let me right. First let me complete the questions from this question and answers box. So from 8:30 I have to see the questions. After that I'll go for attending the questions personally. Right. Sir, what is the difference between MMF and EMF? As I told you that MMF is a magnetomotive force which is responsible to drive the flux. EMF is a electromotive force which is responsible to drive the current. Right? Done. See, please give us time for writing the notes. Okay. I'll share this document to you, but tomorrow onwards I'll give the time to write the notes. Don't worry. Right. Sir, could you please tell about the sequence of topics which definitely Baba Balakrishnan. See, first we'll be discussing about the rotating magnetic field. After that, the detailed construction of an induction machine. After that, we'll be discussing the working principle. I'll list out step by step tomorrow. After that, finding out the performance parameters. After that, we'll be discussing the starting methods, speed control techniques, like other miscellaneous I'll be discussing. So I'll be writing in steps what are the sequence. Don't worry. Explain the concept. We'll discuss after the break. Okay. Introduction, sir. I'll introduce. Don't worry. See, I told you that construction is same. Why? Because maybe motors or generator. So we need magnetic field and we need a conductors or the coils. So when the coils are moved under a magnetic field, it will act as a generator. If I pass a current to the conductor, it will act as a motor. See, I don't have any Telegram group, right? Sir, RMF present in induction generator, yes. Right hand, sir, right hand to know the direction of EMF, left hand rule is to know the direction of motion, rotation. Video struck. We'll see. Right. I'll rectify that. See, I'm moving the screen now. You can see the screen is moving. Right. Anyhow, I'll try to rectify. Maybe, see, I stay in Vijayawada, major center I'm staying. We'll see what is the problem. Okay. Sir, show me the videos. Tomorrow I'll show the videos on this RMF also. Don't worry. Kiran. Well, sir, concept we discuss after the break once, sir. I'm clear with the topics, but after the break, I'm not. Okay, don't worry. I'll explain, Baba. Okay, little bit disturbance means before to this break there was AC, but I have switched on fan now. Maybe small voice. So tomorrow onwards we'll have a full AC. Don't worry. What is the main role of induction motor, sir? See, everywhere we are using induction motor. If we just raise your hand, you can see the fan. We are using induction motor. If you go to water lifting, you have induction motor. If you go to agriculture, induction motor. If you go to office, induction motor. If you talk vacuum cleaner, induction motor. If you go to refrigerator, induction motor. Everywhere you are having induction motor role. Why induction motor is a single excited, right? Why? Because why induction motor is single excited? Why? Because whatever the current that flows in the rotor circuit is due to induction principle. Just like in case of your transformer, the secondary current is due to induction, the rotor current is also due to induction. That is the reason. So there are two magnetic circuit. One is the stator magnetic circuit, the other one is the rotor magnetic circuit. So rotor currents are due to induction principle. That is the reason it is called as single excited. We are using only one source. I'll explain that, don't worry. Sorry, Vishnu, right, we'll see. So groups you can make it. So I'll give my number. So if you are having a group, you can add me. So you can just throw the questions if you are having. I'll give the answers for that, right? No, no issue. So voice is clear, voice is clear. Right, I'll introduce, right? So most of you want to know induction generator applications. Yes. So induction generators will be used in your wind turbines. Variable speeds will go for induction generators. See, all these are the detailed classes which we need to discuss in the coming days. So today we have discussed very basics, right? So let me introduce myself as most of the students need. So I am Dr. Sheikh Abdul Ahad, right? My name is Sheikh Abdul Ahad. So completed my masters from NITK Surathkal and PhD from NITK Surathkal in the year 2003. Since then, I was like working as a professor. Initially, I worked in Vijayawada. Now, presently, I'm working in Hyderabad. I'm associated with our organization, ACE Engineering Academy, since 2008 onwards, more than a decade. So, since 2009 onwards, I'm teaching the same induction machines at Hyderabad and also in other branches of our ACE Academy, like Delhi, wherever I go. So with respect to our academy, I used to teach only induction machines, and outside of Hyderabad, I used to teach other machines also. But in college, I used to teach the other subject, power electronics. Previously, I taught power systems, right? Drives, digital signal processing, digital image processing, then the advanced topics in power electronics, right? Advanced power electronics, drives, right? So mostly I have covered maximum. Why? Because I'm having more than 10 years in teaching experience, right? So as of now, this introduction is enough. So when I complete our course, I'll give a detailed introduction about me, right? So this is something about my introduction. Now, as of now, we need to have discussion time, doubts discussion. So we'll see. I'll spend the time for discussion. So please So one by one, we'll see. So those who are having any doubts, raise the hands. Right. So first, Jichendra.
Hello.
Hello, Jichendra.
Good
You're
evening,
from
sir. Sir, I'm
very
from Haryana.
Haryana. Jichendra, very good evening. Bol Baba, what do you want?
Sir, I'm facing this problem that your voice is breaking so many times in between, and I talk to other students also on group, and many were having this problem.
See, Baba, one thing. See, when I spoke to our host, so he told that the voice is clear, but still, if it persists tomorrow also, so I'll do one thing. So I'll just shift all my settings to near to that Wi-Fi. So my Wi-Fi is in the next room. So maybe due to that Wi-Fi issue, we may have an issue. So tomorrow I'll bring that Wi-Fi next to my system. We'll check. What,
Yes, sir.
Jitendra? Is it clear?
Yes, sir.
Right.
Yes, sir.
I'll try
Thank
to.
you.
Right.
Yes, sir. Thank you so much,
Good,
sir.
Baba. Thank you. Thank you, Baba. Thank you. Right. Next, Vikrant. Vikrant.
Sure.
Vikrant.
So good evening, sir. I'm from Andhra Pradesh, Yeluru.
Cheppamma, Vikrant. You are from Eluru. Vikrant. What?
సార్ అది మనం బ్రేక్ తర్వాత డిస్కస్ చేసిన టాపిక్ ఒకసారి చెప్తాను సార్.
So you mean to say that whatever the topics we have discussed after the break, you want me to repeat once, right?
ఎస్
Right.
ఎస్ సార్.
See, after the break, we have discussed about the rotating magnetic field. So how to produce a rotating magnetic field? Why? Because the heart of induction motor or induction generator is the rotating magnetic field. So we need to produce a rotating magnetic field. So first of all, I have introduced what is called as a rotating magnetic field. You take a magnet, connect that magnet to some external prime mover, and you rotate that magnet. The nature of that magnetic field will be rotating, but it is an uncontrolled one. So the other way of producing a magnetic field is designing an electromagnet, right? So you take a core, on the core you place a coil, and through that coil you pass a current. Then you can see the field will be rotating if you rotate that electromagnet. In both the cases, we are rotating the core, but whatever the rotating magnetic field we are supposed to produce here, it is not with respect to rotating core. The core should be stationary and the winding should be stationary. So if I want to produce a magnetic field, I need the driving force for the magnetic field. What the driving force for the magnetic field means? The current carrying coil. So initially, how many coils we are taking? 3 coils, and how many currents we are passing? 3 currents. Then with that, we are going to see in the coming days how to produce a rotating field. That will be the next topic. Is it clear, Vikrant?
ఎస్ సార్ ఎస్ సార్. థ్యాంక్ యూ సార్.
Right, ma. Thank you. Next, Pranay. Pranay. No. Next, Imtiaz Pasha.
Good evening, sir.
Good evening, ma. Yeah, please ask your question.
Sir, in that analogical illness, this machine is neither act as a generator nor motor, you said, no, sir?
See, when the rotor speed and the field speed, see, both are same in that particular situation. So there is no mechanical torque, there is no electrical power. So this concept you can get a clarity when I'm talking about the detailed working principle, right? So there you can get a clarity in test.
Okay, sir.
Okay.
But
Yeah, please.
sir, but in synchronous machine, we said that analogical illness, no, sir. Can you say that is a synchronous machine?
In case of synchronous motors or synchronous generator, so the mechanical power or your electrical power will be there only at synchronous speed. Why? We'll discuss that. Why? Because in case of motor at synchronous speed, the stator field and the rotor field both will get locked. As they are locked, then the rotor will rotate with the synchronous speed. In case of generators, unless and until the rotor speed is constant, the frequency of the generator power will not be constant. So there the rotor speed has to be kept constant. But whereas in case of induction motor, as the currents are induced, the rotor speed should be always less than ns. Then only there will be some relative speed there will be some flux cutting, then only there will be some EMF, then only there is some current, then only there is some force, there is some torque. Otherwise, there is no concept of motoring. For that, this has to be less than NS, but that has to be always NS. Imtaz Pasha. Is it clear?
Yes, sir. Yes, sir.
Right, Baba.
Sir,
Ah.
sir, your voice is clear. Your voice is clear, but when you are writing notes, sir, at that time we are lagging the writing.
Yeah, I told one more. Jitendra told the same thing. So tomorrow I'll
Yes, sir.
try to shift that Wi-Fi next to my system. We'll see. We can sort out this problem. Okay.
Okay, sir. Thank you.
Right. Thank you, Baba. Next. Kumar.
Hello, sir. Good evening, sir.
Good evening, Kumar. You can ask.
Sir, here in the slide, P is equal to IE is equal to BL.
Yeah. See.
You can explain that.
Yeah. I'll tell you. See, this is uncontrolled, right?
Yes.
So when your B is uncontrolled, then your E is uncontrolled. Correct?
Okay.
So when you connect a load, there is a current. So when E is uncontrolled, E into I is also uncontrolled. The electrical power is uncontrolled. Correct?
Okay. So there will be IBLV, right?
Yeah, correct. Understood?
Yes. Sir, what is the difference between means you said that because of some permanent magnet, if we do any ferrous material is magnetized, that magnetic strength is less than the electromagnets.
No. See, my intention to tell is you take a big size core, right? And you take a small magnet. And if you try to bring that small magnet closer to some big size core, so with this small magnet, is it possible to align all the dipoles inside?
No, sir.
So is that magnetism of that core is fully utilized?
No, sir.
No. Instead of that, on the same core, if you place a coil, and through that coil, if you pass a current, when you are increasing the current magnitude, the field strength will increase and all the dipoles can be aligned. So the core magnetization can be maximum utilized.
Okay.
Understood, Kumar?
No, I understand.
Right.
Thanks.
Right. Right. I'm attending. I'm coming. Right.
Good evening, sir.
Yeah, good evening, Vaishnavi.
Sir, can you say what is the exact meaning of induction, sir?
See, induction means something like without contact. Okay. Right, you are having induction, right, without contact. Conduction with contact.
Okay. Sir, understand, sir. Sir, in Fleming right hand rule, once you show that page, sir, in Fleming's right hand rule, starting.
Yeah, I'm trying to open, just wait. This figure, right?
So before that, sir, Fleming's right hand. Here, sir, somewhat down, sir. Down, sir. Sir, you shown one figure, no, sir. Clockwise, the conductor will rotate it. The conductor will rotate in clockwise. You shown EMF direction, no, sir.
So here, if the conductor is moving clockwise direction, so the direction of induced EMF, I have shown it as cross. It is into.
Sir, it will be here. Both force. Sir, ikkada flux lines, flux direction, conductor down up. Appudu EMF perpendicular ga undali కదా sir. EMF.
అవునమ్మా, ఎగ్జాక్ట్లీ కరెక్ట్. అందుకే చూసాక పర్పెండిక్యులర్ గానే ఉంది అది. సో ఇక్కడ ఈ అనేది చూసా పర్పెండిక్యులర్ అని డ్రా చేశానమ్మా నేను.
ఓకే, అదే సార్, అంటే కొంచెం యాంగిల్ లాగా ఉంటే.
లేదు నాన్న, పర్పెండిక్యులర్ తల్లి. ఓకే,
ఓకే
రైట్ అమ్మా, రైట్.
సార్ ఇంకొకటి సార్, ఫ్యూచర్స్ లో సెకండ్ పాయింట్ చెప్పారు కదా సార్, సింగిల్ ఎగ్జైటెడ్ మిషన్ యాజ్ ట్రాన్స్ఫార్మర్ అని.
అవునమ్మా,
అది ఒకసారి చెప్పరా సార్?
ఇప్పుడు ఇండక్షన్ మోటార్లో కూడా మనకి ఏముంటుందంటే అమ్మా, సో విల్ హ్యావ్ ఎ స్టేటర్ with a 3-phase winding, will be having a rotor. How many magnetic fields are required even for induction motor? 2 magnetic fields. So one magnetic field is produced by giving a 3-phase excitation to stator, IA, IB, IC. One field, we call it as stator field. This field, as it is rotating, this cuts the conductor and EMF is induced. This EMF will circulate a current in the rotor conductors. Because of the current, there is one more flux. We call it as rotor flux. That we'll see. The rotor flux is due to separately excited currents, or it is due to induced current, means it is due to induced current. So altogether, how many sources we are using here? We are using only one 3-phase to stator. No source we are using to excite the rotor. So the rotor windings are excited with induced current. Just like in case of transformer, you can see the secondary windings are excited with the induced current. Here also the rotor windings are excited with induced current. So how many sources we are using for induction means there is only one source to excite the stator winding. But how the rotor windings are excited means due to that induced current. So that is the reason it is called as a induction motor, or it is called as a single excited motor. Only one 3-phase source we are giving to stator circuit. Is this point clear?
ఎస్ సార్, క్లియర్ సార్. ఇంకొక చిన్న డౌట్ సార్, ఇప్పుడు కండక్టర్ గానీ మూవ్ అయితే ఫ్లక్స్ అనేది కట్టింగ్ అవుతుంది అని చెప్తాము. ఒకవేళ ఫ్లక్స్ గానీ వేరీ అవుతూ కండక్టర్ లోకి వెళ్తే ఫ్లక్స్ చేంజ్ అవుతూ కండక్టర్ లో ఈఎంఎఫ్ ఇండ్యూస్ అవుతుంది అని చెప్తాం, అంతేనా సార్?
అంతే అమ్మ, కరెక్ట్.
ఓకే సార్,
రైట్.
థ్యాంక్ యూ.
ఫ్లక్స్ లింకేజెస్ మారుతున్నాయమ్మా. మెయిన్ ఫ్యాక్టర్ ఫ్లక్స్ లింకేజెస్ షుడ్ చేంజ్. ఓకేనా?
ఓకే సార్,
రైట్ అమ్మ,
థ్యాంక్ యూ సార్.
రైట్ అమ్మ. రైట్. అనిల్. 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 నెక్స్ట్. Anil.
Hello, sir. Good evening, sir.
Good evening, Anil. Just please.
Am I audible, sir?
You are audible, Anil. Please ask.
Sir, I have a small clarity about lens law, sir.
Yeah, please ask, Anil. I'm there. I'll explain your doubt in lens law. Yeah.
Yes, sir. Can you please open the slide?
See, you can see the same thing is on the board.
Yes, sir. Yes, sir. In this second case, can you explain once again?
See, in the I'll explain. In the second case, the magnet is very close, right?
Okay, sir.
When the magnet is very close, whatever the flux linkages with that coil, maximum.
Maximum.
Yeah. If that magnet is there for long time, so there is no change in the flux line. The total flux lines are maximum, correct?
Yes, sir.
But when I try to move this magnet back, then what happened to the number of flux lines? Will decrease. Or they will decrease?
Decrease.
Right? When they are decreasing, nothing but they are changing, right?
Yes, sir.
When they are changing, what is induced?
EMF induce.
What circulates?
Current.
Because of that current, there has to be one more flux. What should be the role of that flux? It has to increase the flux lines, or it has to decrease the flux lines? They were maximum. As the magnet is moving away, they start decreasing. So to keep the flux lines constant, so the direction of field should be in the same direction or opposite direction?
In the opposite direction, sir.
If it is in opposite direction, flux will decrease, na? As the flux lines are moving back, the total flux lines through the coil are decreasing. But the total flux line should remain constant. Why? Because the flux line should remain maximum. So for that, what should be the total flux line should remain constant? What should be the direction of flux? It should be in the same direction or opposite direction?
Same direction, sir.
Same direction. For that, what should be the direction of current? It should be from A to B. Apply right hand thumb rule so that the flux lines will be upward direction. Anil.
Okay, sir. Understood, sir.
Understood?
Yes,
So
sir.
if the flux lines are decreasing, to aid that, the flux line should be in opposite direction. As they are going back, so they should be in the opposite, means it should be in the same direction to add that. Understood?
Okay, sir. Sir?
Right.
Sir.
Yeah, Anil, please.
Initially, చేంజ్ ఇన్ దట్ లింకేజ్ ఆఫ్ చేంజ్ లింకేజ్ అనేది ఎంత ఉంటే మనకి తర్వాత ఎఫెక్ట్ వచ్చిన తర్వాత కూడా మళ్ళీ అంతే ఉండాలి సార్.
Ante, correct. So whatever the flux we have in the initial state, even after the effect, the flux should remain same. If it
Okay,
is
sir.
zero, it should remain zero only. If it is maximum, it should remain maximum. For that, the EMF act as accordingly to produce a current.
Okay, sir. Sir, along with I have another doubt.
Understood?
Yes, sir. Yes, sir.
Yeah.
I have another doubt, sir. In Lorentz law,
Yeah, you can ask Anil.
hello, sir. Yes, sir. In Lorentz law, can you please open the slide?
Yeah, you can see it is.
Yes, sir. Below, sir. The magnetic lines are curved, sir. Why it is like?
Why? Because between the magnetic field lines always repulsive forces. No magnetic field lines will intersect. Just like your railway track lines cannot intersect, they will always try to repel. So here you can see, because of this current carrying conductor, there is one more set of magnetic flux lines. So they cannot take the straight path here. So they will be taking the longest path. Why? Because the flux lines are occupying this path. Correct?
బట్ జనరల్లీ ఇక్కడ మనకి కండక్టర్ చుట్టూ ఉన్నటువంటి ఫ్లక్స్ లైన్స్ నార్మల్ గా ఉన్న ఫ్లక్స్ లైన్స్ ఒకే డైరెక్షన్ లో ఉన్నాయి కదా సార్.
Okay, కానీ see, ఇప్పుడు ఈ these flux lines are traveling, they cannot take the path. Why? Because there is always repulsive force. When there is a repulsive force, in which direction they will take now? So they will take the curve path only. So if the direction of current in this is
ఓకే సార్, నౌ ఐ అండర్స్టూడ్. అంటే సేమ్ డైరెక్షన్ లో ఉంది కాబట్టి ఇది నార్త్ పోల్ అయితే ఇది నార్త్ పోల్ యాక్ట్ అయ్యి రిపల్షన్ అవ్వడం వల్ల మనకి కొంత స్లైట్ గా కర్వ్ అవ్వచ్చు,
కొంచెం మూవ్ అవుతుంది. కరెక్ట్, అంతే. ఓకేనా
సార్? అలాంగ్ విత్ ఐ హావ్ సమ్ నెట్వర్క్ ఇష్యూ వైల్ వి ఆర్ టేకింగ్ ఫీచర్స్ ఫస్ట్ పాయింట్. Can you please explain once again?
I'll send the notes, don't worry. See,
Okay,
features first point means it is a single excited machine. Right, sir? This is what is that? First point is it works on mutual induction principle. Why? Because the current flows in the rotor is due to induction principle. So that is the reason it is called as induction motor. Why?
Okay,
because
sir.
we are not giving any extra source to supply the current. Understood?
Understood, sir.
Right.
This
right,
is only discussed, sir.
This that is the only point which I have discussed. Understood?
Okay, sir. Thank you, sir. Thank you, sir. Thank you.
Right, ma. Right. Next. Yes.
The motor
Hello?
works on induction principle, junction line and transformer.
See, your voice is not audible, ma. Please, can you speak clearly?
Sir, I'm audible now.
But there is something like mixing up of voice.
Now, sir.
Yeah, please. Clear.
Sir, the motor works on induction principle, junction line, transformer. Sir, is it?
See, this induction motor also called as a rotating transformer. Why? Because in case of transformer, the secondary is stationary, right? But whereas in case of induction, the rotor is the secondary, which is a rotating. That is the reason it is called as a rotating transformer also. Understood?
Junction line and the rotated transformer is same అంటున్నారు.
నీ మాట అర్థం కావట్లేదు అన్న. సో ఇప్పుడు ఇండక్షన్ మోటారు, హలో ఒకసారి అడగమ్మా మళ్ళీ.
సార్, మోటార్ వర్క్స్ ఇండక్షన్ ప్రిన్సిపల్ జంక్షన్ లైన్ అంటున్నారు కదా సార్?
కాదమ్మా, ఇప్పుడు మోటార్ అని ఇండక్షన్ మోటార్ ప్రిన్సిపల్ కూడా లోరెన్స్ లానే. లోరెన్స్ లా, వాట్ ఈస్ దట్? లోరెన్స్ లా సేస్ దట్ F is equal to BIL. So the current carrying conductors has to place under magnetic fields. Okay, లోరెన్స్ లానే. కానీ ఇప్పుడు ఈ I ఏదైతే ఉందో ఇక్కడ I, whatever that I we have in that equation, that I is due to induction principle. So that is the reason it is called as an induction motor. Yogashri, understood? What is your doubt?
Sir?
What is your doubt?
అక్కడ నాకు కొంచెం బ్రేక్ అయింది సార్ మీరు చెప్పేటప్పుడు. అది జంక్షన్ లైనేనా కాదా అని అడుగుతున్నాను సార్.
జంక్షన్ లైనా?
ప్రిన్సిపల్ దగ్గరే మీరేమో రాశారు కదా సార్ లైన్ జంక్షన్.
నేను ఒక్క నిమిషం వస్తానన్నా. జస్ట్ వేర్ ఇట్ ఈస్
సార్ పైన సార్.
ఒక్కటి నాన్న, ఒక్క నిమిషం నాన్న. ఐ విల్ జస్ట్ మూవ్ అప్.
ఇక్కడ
ఇక్కడేనా?
కిందికి వెళ్ళిపోయారు సార్.
ఇంకా పైకి వెళ్ళాలి.
ఫీచర్స్ లో సార్.
ఫీచర్స్ అంటే ఇదే కదా నాన్న. ఇక్కడ ఇదే కదా. దిస్ మోటార్ వర్క్స్ ఆన్ ఇండక్షన్ ప్రిన్సిపల్ జస్ట్ లైక్ ట్రాన్స్ఫార్మర్.
జస్ట్ లైక్ సార్.
జస్ట్ లైక్ నాన్న, జస్ట్ లైక్ ట్రాన్స్ఫార్మర్.
ఓకే సార్.
ఏం అర్థమైందా?
ఓకే సార్.
రైట్ నాన్న, రైట్.
సార్ ఇంకోటి కంటిన్యూస్ రోటర్ ఇండక్షన్ ఉంది కదా, కంట్రోల్ అండ్ మ్యాగ్నెటిక్ ఫీల్డ్ ఉంది కదా సార్.
అవునమ్మా.
ఒకసారి అది ఎక్స్ప్లెయిన్ చేయరా సార్? అది
ఇది ఇఫ్ యూ టేక్ ఏ పర్మనెంట్ మ్యాగ్నెట్, సో ఈజ్ ఇట్ పాసిబుల్ టు వేరీ ద ఫీల్డ్ స్ట్రెంత్? If you take a permanent magnet, is it possible to vary the field strength?
No sir.
So it is controlled or uncontrolled?
Uncontrolled.
But if you are designing an electromagnet, what is an electromagnet? Core, winding and current. By varying the magnitude of current, we can vary the field strength, we can vary the aligned dipoles, we can vary the magnitude. So are the controlled magnetism or uncontrolled magnetism?
Controlled magnetism.
I hope you understood the difference. Is it clear, ma?
ఓకే సార్.
రైట్ నాన్న, రైట్.
సార్ ఒకసారి మాకు ఇట్లా వీడియో లాగా చూపియారా సార్, ఇంకా కొంచెం మంచిగా అర్థం అవుతుంది అని, క్లారిఫై అవుతుంటాయి.
దీనికి వీడియో లేదమ్మా, RMF ఉంది. ఐ షో టుమారో. ఓకే, ఐ షో ఇట్ టుమారో. రైట్. సో వాట్ ఎవర్
లాకి ఇండక్షన్ మోటార్ కి అవి ఉన్నాయి కదా సార్, వాటికి డిఫరెన్స్ ఏంటిదో అర్థం అవుతుంది కదా సార్ వీడియో రూపంలో, అందుకని అడుగుతాను.
నేను చెప్తాను నాన్న, ఎప్పుడైతే కావాలో నేను చెప్తాను. ఓకే.
ఓకే సార్.
రైట్ అమ్మా, రైట్.
సార్
అరే యా యోగశ్రీ చెప్పమ్మా.
సార్ ఒకసారి టాపిక్స్ అండ్ వెయిటేజ్ ఒకసారి ఇవ్వరా సార్?
ఒక్కటి నాన్న. ఐ విల్ టెల్ ఈచ్ అండ్ ఎవ్రీథింగ్. జస్ట్ గివ్ మీ సమ్ స్కోప్. ఓకే, లెట్ మీ బ్రీత్. ఐ విల్ టెల్. సో ఎప్పుడు చెప్పాలి చెప్తాను నాన్న. ఓకే, లెట్ మీ ఎంటర్. ఐ విల్ టెల్. ఓకే, డోంట్ వరీ. రైట్ అమ్మా, రైట్. హలో 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 అబ్దుల్ రెహమాన్. హలో 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 హలో
హలో
రవితేజ
సార్. గుడ్ ఈవినింగ్ సార్.
గుడ్ ఈవినింగ్ బాబా.
సార్ ఇది లెంజులాలో మీరు డైరెక్షన్ తీసుకున్నారు కదా సార్, అది నాకు ఎలాగో అర్థం కాలేదు సార్.
ఏం లేదు నాన్న. ఇప్పుడు ఇఫ్ యూ టేక్ ద ఫస్ట్ కేస్ ద ఫ్లక్స్ లైన్స్ ఆర్ మినిమమ్ ఆర్ maximum?
మినిమం సార్.
Minimum. So When this north pole is coming closer to that, what happened to flux lines?
Increases.
Increases. But the flux line should remain always initial, whatever the initial condition that is there, that should has to exist. What about the flux lines initially?
Low.
Let it be 0. But when this north pole is coming closer to that, what happened to flux lines?
Increases.
But the flux line should remain again minimum.
Minimum.
So whenever the magnet is coming closer to that, the flux linking with that coil is changing. What is induced?
EMF will induce.
What circulate if the circuit is closed?
The direction of current, I didn't understood.
What flows through that?
Current.
Current. So that current has to produce one more flux. That flux should be in opposite direction or same direction?
Opposite direction.
So the flux should be downwards. If the flux should be downwards, means the flow of current should be from B to A or A to B?
B to A.
B to A. So if the direction of current is from B to A, then flux will be downwards. It will be opposite.
Okay, sir. I understood.
Understood. Right.
Understood. Thank you, sir.
Right, Papa. Right.
Okay.
Right. Abdul Rahman. Abdul Rahman.
Hello, sir.
Yes, Baba, please.
The representation of cross and dot.
Pardon?
Representation of cross and dot.
Representation. That is a general IEEE format to represent the direction of induced EMF. So on what basis we represent this cross and dot means you take an arrow. You know,
Yes,
arrow, tir. If you release that arrow and if you see the arrow from behind,
okay, sir.
so with respect to your eyes, if the arrow is moving away, then what is the symbol you come across?
Cross.
Cross, right?
Yes, sir.
And if the same arrow, if it is approaching towards your eyes, then what is the symbol you come across?
Dot.
Dot. So assume that this is your book.
Okay.
In the book, there is one conductor like this. Inside, there is one conductor like this.
Okay, sir.
If you are putting cross in that book, means the flow of current is into or outwards?
Into.
That means with respect to your eyes, the current is flowing away. That is into the book.
Yes, sir.
So if you are putting dot, means the current is coming out of the book. It means it is coming towards your eyes.
Yes, sir.
Now it is clear?
Yes, sir. Yes, sir.
Right.
Thank you.
Right, Baba. Next. Bharat.
Good evening, sir.
Good evening, Baba.
Sir, in Lorentz law, why explains the force?
Why? Because
Please.
it is experimentally proved that if you place a current carrying conductor, it will experience a force. It is experimentally proved. But what is the main reason for that? Lorentz?
सर आपने
हाँ बाबा वही बता रहा हूँ अभी.
हाँ आपने बोला था ना कैसे किसी ने पूछा तो एक्सपीरियंस हो.
हाँ वही बता रहा हूँ अभी.
ओके.
जब कंडक्टर में कुछ करंट नहीं है, then what will be the direction of flux lines? They are coming straight forward. They are taking the low reluctance path, right? But whenever we pass a current to that conductor, what happened? Due to that current carrying conductor, there is one more flux surrounding the conductor. So because of this one more flux which is surrounding the conductor, the original flux lines which are coming from north pole will divert themselves. Why? Because between the lines there is always repulsive force, right? They cannot take this path, so they have to divert. But when they are diverting, they are taking more length in air. So when they are taking more length in air, so the reluctance of that path is increased. So the magnetic flux lines cannot take the long path when there is a short path available. So what is the short path available? The straight path. But why the straight path they are not taking means because of the conductor which is carrying current. So they'll push, or you please move, repulsive force will be there. Then that conductor will be moved. Again, they'll come back to their original paths. Understood now?
Okay, sir. Understood.
Right.
Thank you.
Right. Okay. Bhaskar.
Hello, good evening, sir.
Yeah, good evening, Bhaskar, please.
Sir, in controlled magnet, how the positions of dipoles?
Yeah, please ask, ma.
Sir. Hello.
Your voice is not clear. Bhaskar, your voice is not clear.
Hello, sir.
Hello, I can hear you. Please, Bhaskar, speak.
Sir, in controlled magnet, how? Hello.
Yeah, please ask the question.
In controlled magnet, how the positions of dipoles, sir?
That I'll tell you in the concept of pole formation. Don't worry. So why there is a north pole, why there is a south pole, right? Your question?
Yes, sir.
So it is simple right hand thumb rule.
Okay, okay, sir.
You apply the right hand thumb rule, you'll get the answer for that. Okay. I'll just wait 1 second, I'll show. So if you take this, if you place the 4 fingers, you can see on the board 4 fingers. So
Yes,
in the
sir.
direction of current. So with respect to this, the magnetic field lines will be like this. If you imagine a north pole and a south pole, if the magnetic field lines are coming out, then what is the pole that can be imagined there?
Okay, sir. North pole. Hello.
And this is the south pole.
Okay, okay, sir.
Understood?
Okay, sir. Sir.
Right.
Sir.
Yeah, please. Hello. Yeah. Hello.
Good evening, sir. Good evening, sir.
Good evening, ma.
Sir, once explain today's last topic,
Good evening,
sir.
ma.
Sir, once explain today's last topic, sir. The
Last.
circuit
See,
consisting.
if I want to pardon.
Sir, last topic, sir. The circuit consisting of some flowchart will be.
See, if you want.
Sir, this one.
See, if you want to have flux, what is the driving force for the flux?
Sir, from the starting explains. Sir.
See, your voice is not clear, ma. See,
Sir,
if
from
I want
the starting
to,
explain Jayara.
This electric circuit nundamma.
Yes, sir. Yes, sir.
If I want to have current in electric circuit, what is the driving force? EMF.
EMF.
What are the various sources of EMF? Battery and
batteries.
Conductor moved under a magnetic field, correct?
Yes, sir.
If I want to have flux in a magnetic circuit, if I want to produce magnetism, what is the driving force?
MMF.
What are the various sources of MMF? One is a permanent magnet, the other one is a current carrying coil, correct?
Okay.
Current carrying coil. I should know.
Okay, sir.
So
Thank
how
you.
many coils you are taking now? 3 coils. Right, ma, right.
Okay.
Right. So one Kumar was like raising the hands. So he's not there. Anyhow, I'll stop for today. So we'll meet tomorrow. Right. Thank you.